Dr. Pepper's factory process is much more complex than other sodas. Many people think they know how it's made, but when you truly dive in, the actual process exposes exactly what Dr. Pepper does differently compared to the competition. Today, we're diving into how Dr. Pepper, Coca-Cola, and orange juice are made. Dr. Pepper comes to life the instant a stream of invisible carbon dioxide disappears into an ice-cold beverage, because everything that happens afterward depends on keeping that gas trapped until the very second the bottle or can is opened. The carbonator sits at the center of the production line, receiving a chilled, completely flat drink from the blending system. At this stage, the beverage already has its sweetness, acidity, color, and signature flavor profile, but it has no sparkle. Inside the sealed vessel, carbon dioxide enters under carefully controlled pressure. Instead of forming large bubbles, the gas breaks into microscopic pockets that dissolve into the liquid. Within moments, the beverage becomes fully carbonated, transforming from a still drink into Dr. Pepper. That invisible transformation only works because of everything that happened before it. Long before carbonation begins, treated water enters the factory through stainless steel pipelines. Water makes up the majority of the finished beverage, so every batch starts here. The incoming supply passes through multiple treatment stages designed to create a consistent foundation. Fine filtration removes suspended particles. Activated carbon beds reduce unwanted taste and odor compounds. Additional polishing systems stabilize the water before it reaches large storage tanks. The treated water leaves storage only when the blending system calls for it. Pumps move the clear liquid toward the syrup preparation area, where another process has already been underway. Inside a separate mixing vessel, sweetener forms the backbone of the syrup. If granulated sugar is used, controlled feeders deliver measured quantities into circulating treated water. Powerful agitators keep the liquid moving while the sugar dissolves. At first, individual crystals swirl through the tank. Gradually, they disappear until the liquid becomes completely uniform. If liquid sweetener is used instead, it enters through heated stainless steel lines. Flow meters continuously monitor the addition, ensuring every batch matches the previous one. Regardless of the sweetener source, the objective remains identical. Produce a perfectly uniform sweet base with no undissolved solids. The sweet base travels through filtration before anything else is added. Even tiny particles could interfere with precision flow meters, pumps, or filling equipment later in the process. Once filtered, the syrup moves toward the blending vessel, where the drink begins developing its recognizable identity. Now comes one of the smallest additions in volume, but one of the biggest changes in character. The concentrated Dr. Pepper flavor system enters through enclosed dosing lines. Only a carefully measured amount is needed because it is highly concentrated. As it enters the circulating syrup, darker ribbons briefly appear before disappearing into the moving liquid. The entire tank gradually changes into a deep brown concentrate that now contains sweetness, acidity, color, and the complex flavor profile that defines the beverage. Despite its appearance, this still is not Dr. Pepper as consumers know it. The syrup is far too concentrated to drink. It exists only as a compact version of the final beverage. After blending, the syrup enters insulated holding tanks equipped with slow-moving agitators. These paddles rotate gently, preventing heavier ingredients from settling while avoiding unnecessary air incorporation. Level sensors monitor the remaining volume continuously, so the production line always has enough concentrate available. Soon, the syrup begins its journey toward the proportioning system. Meanwhile, treated water follows a completely separate route toward the same destination. Two independent streams, one clear, one dark, approach the blending skid from opposite directions. Electronic flow meters measure both streams thousands of times every hour. Computer-controlled valves constantly make tiny adjustments. If production speeds increase, both streams accelerate together. If demand slows, they reduce proportionally. Maintaining the precise syrup-to-water ratio is essential because every bottle leaving the line must taste identical. Inside the proportioner, the concentrated syrup merges with treated water. Almost instantly, the dense concentrate disperses throughout the much larger water stream. The beverage now reaches its final drinking strength. It still lacks one defining feature. The beverage leaves the proportioner completely flat. Before carbonation can begin, temperature must change dramatically. The freshly blended drink enters a plate heat exchanger where thin stainless steel plates separate the beverage from a chilled cooling medium. Heat transfers rapidly through the metal surfaces. Within seconds, the beverage temperature drops substantially. This colder temperature prepares the liquid for something impossible at warmer conditions. Carbon dioxide dissolves far more effectively in cold liquid. Before the gas enters, another hidden process often takes place. The beverage passes through a deaeration stage where dissolved oxygen and unwanted air are removed. Tiny gas pockets separate from the liquid under carefully controlled conditions. Removing these gases improves carbonation efficiency and helps maintain long-term product stability. Only after chilling and deaeration does the beverage finally reach the carbonator. Inside the sealed vessel, carbon dioxide enters through specialized diffusers. Pressure builds while the beverage continues flowing. Rather than forming visible fizz, the gas dissolves directly into the cold liquid. The beverage still appears calm, but its internal chemistry has completely changed. From this moment forward, every machine on the line has one mission: never allow that dissolved gas to escape. The carbonated Dr. Pepper flows through sealed stainless steel pipelines maintained under pressure. Sharp turns are minimized. Sudden pressure drops are avoided. Smooth piping reduces unnecessary turbulence. While the beverage travels toward filling, empty containers begin an entirely different journey. PET bottles often begin as small plastic preforms. These thick test tube-shaped pieces already contain the finished bottle neck and threaded opening. Their bodies, however, remain compact. Preforms enter a heating oven where rows of infrared lamps warm only the body section while the neck stays cool. Every preform rotates continuously, ensuring even heating around the circumference. Once softened, each preform moves into a blow mold. The mold closes instantly. A stretch rod pulls downward through the center, while high-pressure compressed air expands the softened plastic outward. The material stretches until it contacts every detail inside the chilled mold cavity. Base, shoulders, sidewalls, and label panels all appear within seconds. The finished bottle exits remarkably lightweight, yet surprisingly strong. Air conveyors transport empty bottles by supporting only their neck rings. Jets of filtered air propel them rapidly through the system while preventing contact with sidewalls. Before filling, each bottle passes through an internal rinsing station. Bottles invert, receive filtered air or treated rinse water, drain immediately, then rotate upright again. Aluminum cans follow a different route. Already formed and decorated, empty cans arrive stacked on pallets. Depalletizers unload entire layers before guiding individual cans into high-speed conveyors. Each can inverts through an air or water rinser to remove any loose particles. After draining, the cans continue upright toward the filling carousel. Now both product streams finally meet. Inside the rotary filler, containers travel in perfect synchronization beneath filling valves. For bottles, each neck seals tightly against its valve before filling begins. Pressure inside the bottle equalizes with pressure inside the filler bowl. Without this equalization, dissolved carbon dioxide would immediately burst out of solution, creating excessive foam. Once pressures match, the valve opens. Dr. Pepper flows smoothly into the bottle. The dark liquid rises rapidly, while only a controlled amount of foam develops near the surface. Electronic controls determine the exact fill level before the valve closes. Each filled bottle immediately transfers toward the capping turret. Caps travel through sorting bowls that orient every closure correctly before delivery to spinning capping heads. Each head applies precisely controlled torque, tight enough to seal carbonation, not tight enough to damage threads. Aluminum cans move directly into the seamer. Lids drop onto each filled can moments before rotating beneath seaming rollers. The first roller folds the lid curl around the can flange. The second roller compresses both layers into a tightly interlocked double seam. No glue is used, only precisely folded metal holds the internal pressure. Now another important checkpoint arrives. Sophisticated inspection systems immediately verify every package. Vision cameras examine fill height, cap alignment, tamper bands, seam profiles, dents, scratches, and container deformation. Coca-Cola disappears into an empty bottle before anyone ever sees the most important transformation, because by the time the liquid reaches the filling machine, nearly every critical step has already happened behind sealed stainless steel walls. The beverage rushing toward the filler is already cold, already carbonated, and already balanced to its final drinking strength. It travels through polished pipelines under carefully maintained pressure, moving quietly despite carrying millions of dissolved carbon dioxide molecules that are waiting for a chance to escape. Every valve, every bend, and every pump between the blending room and the filling carousel has one responsibility: protect that carbonation. A sudden pressure drop would instantly create foam, waste product, and destroy fill accuracy. The entire production line is built around preventing that from happening, but to understand why, the process has to rewind to where Coca-Cola begins as nothing more than treated water and concentrated syrup. Water enters the factory continuously through large stainless steel supply lines before passing into an extensive treatment system. Since water makes up the overwhelming majority of every bottle and can, consistency is everything. The incoming supply first moves through coarse filtration that removes suspended particles before entering activated carbon filters that eliminate unwanted tastes and odors. Depending on the facility, additional polishing systems refine mineral balance and clarity even further. Storage tanks hold this purified water under controlled conditions until production demands it. Although the water appears unchanged to the eye, it has become a carefully standardized ingredient capable of producing identical batches every hour of every day. While treated water waits in storage, another process unfolds in the syrup room. Massive blending vessels begin filling with measured quantities of sweetener. If granulated sugar is used, controlled feeding systems deliver it steadily into circulating water. The crystals disappear as powerful agitators rotate beneath the surface, creating a dense syrup that grows thicker with every passing minute. In facilities using liquid sweetener, insulated pipelines deliver the ingredient directly into the tanks, while electronic flow meters continuously verify every addition. Regardless of the sweetener source, the objective remains identical: create a perfectly uniform foundation before a single drop of flavor concentrate enters the mixture. The syrup becomes glossy, heavier than water, and completely free of undissolved solids before moving forward. Only after the sweet base reaches the required consistency does the next stage begin. Concentrated Coca-Cola flavor is introduced through enclosed dosing systems designed for exceptional precision. Compared with the volume of sweet syrup already inside the tank, the concentrate represents only a small fraction of the batch, yet it transforms everything. Dark ribbons briefly appear as the concentrate enters the circulating liquid before disappearing into the constantly moving current. The color deepens almost immediately, changing the once clear syrup into a rich brown concentrate. Acidity, color, and the signature flavor profile spread throughout the vessel until every portion matches every other. Even now, however, the mixture bears little resemblance to the finished drink because it is still far too concentrated to consume. The completed syrup moves into insulated holding tanks equipped with slow-turning agitators. These paddles are intentionally gentle. They keep ingredients evenly distributed without introducing unnecessary air into the mixture. Sensors constantly monitor temperature, liquid level, and transfer rates, while automated pumps respond whenever the production line requests more concentrate. On the opposite side of the blending system, treated water begins its own journey toward the proportioning unit. Two completely separate streams now travel toward a single destination, and this is where the beverage finally begins taking its recognizable form. Inside the proportioning system, electronic flow meters monitor both liquids continuously. One stream carries dense concentrated syrup, while the other carries crystal clear treated water. Computer-controlled valves make tiny adjustments hundreds of times each minute, compensating for changing production speeds without allowing the ratio to drift. The two liquids meet inside enclosed blending chambers, where the syrup disperses almost instantly throughout the much larger water stream. Within seconds, the beverage reaches its finished sweetness, acidity, color, and flavor intensity. It finally tastes like Coca-Cola, but something essential is still missing. At this point, the liquid is completely flat. There is no sparkle, no hiss, and none of the crisp sensation associated with opening a fresh bottle. Before carbonation can begin, temperature must change dramatically. The beverage enters a plate heat exchanger constructed from stacks of thin stainless steel plates. Cold coolant flows along one side of each plate while the beverage flows along the other, allowing heat to transfer rapidly through the metal without the two liquids ever mixing. Within moments, the drink exits several degrees colder than when it entered. This cooling stage is critical because cold liquid absorbs carbon dioxide far more effectively than warm liquid, while also reducing foam during filling. Hidden inside this seemingly simple temperature change is one of the biggest factors determining how lively the finished beverage will feel. Many production lines include another important step before carbonation begins. Dissolved oxygen and unwanted gases are removed through deaeration equipment operating under carefully controlled conditions. Tiny air bubbles separate from the liquid before escaping through the system, leaving behind a beverage better prepared to accept carbon dioxide. Although invisible to anyone watching the conveyor outside, this stage improves carbonation performance and helps preserve long-term flavor stability. Only after chilling and deaeration does the beverage finally approach the machine responsible for one of the factory's most dramatic transformations. Inside the carbonator, chilled Coca-Cola meets carbon dioxide under pressure. The gas enters through specialized diffusers that create enormous surface area while maintaining complete control over pressure and flow. Instead of forming visible fizz, the gas dissolves directly into the liquid. The beverage leaving the vessel looks almost identical to the flat drink that entered moments earlier, yet internally, everything has changed. Millions of microscopic carbon dioxide molecules are now held inside the cold liquid under pressure, waiting for the instant that pressure disappears. From here onward, every section of the production line focuses on preserving those dissolved gases until the package is completely sealed. At exactly the same time, empty containers begin their own journey toward the filler. Plastic bottles usually start as compact PET preforms that resemble thick test tubes with finished bottlenecks already molded into place. These preforms travel through infrared heating ovens, where they rotate continuously, allowing heat to soften only the body while leaving the threaded neck cool and dimensionally stable. Once heated, each preform enters a blow mold, where a stretch rod pulls downward through its center, while high-pressure compressed air expands the softened plastic against chilled mold walls. In only a few seconds, the compact preform becomes a full-sized Coca-Cola bottle, complete with base contours, shoulder profile, grip panels, and label area. Aluminum cans follow a completely different route. Already formed and printed before arriving at the beverage plant, they are unloaded from pallets by automated depalletizers before entering high-speed conveyors. Every empty can passes through a rinsing station where filtered air or treated water removes dust and loose particles. Bottles undergo similar internal cleaning after blow molding, ensuring every container reaches the filler clean and ready to receive the finished beverage. Now both production streams finally meet at the rotary filling machine. Empty bottles and cans enter through synchronized style wheels that position each container beneath an individual filling valve. The filler itself rotates continuously while maintaining pressure inside its enclosed bowl. For bottles, the valve seals tightly against the neck opening before internal pressure equalizes with the pressure inside the filler. This single step prevents dissolved carbon dioxide from escaping violently as filling begins. Once pressure is balanced, the valve opens and Coca-Cola flows smoothly into the container. The dark liquid rises rapidly while only a carefully controlled amount of foam forms near the surface. Sensors monitor fill height precisely before each valve closes at exactly the programmed level. The filled containers move immediately toward closure because every fraction of a second matters once carbonation has entered the package. Plastic bottles receive caps supplied through vibrating sorting bowls that orient every closure correctly before feeding rotating capping heads. Each cap tightens to a carefully controlled torque that seals carbonation securely without damaging bottle threads. Aluminum cans instead travel into seamers, where lids drop into position before precision rollers fold the lid, curl around the can flange. Two separate roller operations create the finished double seam, mechanically locking multiple layers of aluminum together into a pressure-resistant seal without requiring adhesive. Inspection begins immediately after sealing. Vision systems examine fill height, cap alignment, tamper bands, seam quality, dents, scratches, and container deformation, while laser sensors verify liquid levels. Automated reject systems remove any package falling outside specification without slowing production. Cold filling leaves moisture condensed across container surfaces, so powerful air knives blast away water before labeling and secondary packaging begin. Plastic bottles move through labeling equipment where printed film unwinds continuously from large reels. Registration sensors track alignment marks before rotary knives cut individual labels. Adhesive secures the leading edge while spinning bottles wrap the remaining label tightly around their bodies. Pressure rollers smooth every wrinkle before the bottles continue toward coating. Shrink sleeve formats instead receive loose sleeves that tighten around the bottle inside heated tunnels, perfectly matching every contour as the film contracts. The final stages transform individual containers into retail-ready products. Guide rails divide the conveyor into multiple lanes before timing screws establish exact spacing for grouping. 6-packs, 12-packs, and larger configurations form automatically before shrink film or paperboard cartons surround the containers. Heat tunnels tighten shrink film into compact bundles, while cartoning equipment folds and seals printed paperboard around grouped bottles or cans. Every finished pack passes another inspection stage, verifying count, orientation, coding, and package integrity before entering corrugated shipping cases. Tropicana orange juice begins changing long before it ever reaches a bottle, because the most valuable part of the fruit is separated only seconds after the peel is broken. Fresh oranges arrive at the processing facility in enormous loads before moving onto wide receiving conveyors that feed the first stage of production. Leaves, small branches, and loose debris are removed immediately as the fruit passes beneath air blowers and over-sorting equipment. From there, thousands of oranges travel through long washing channels where powerful sprays and rotating brushes scrub every piece of fruit from multiple directions. Dirt, dust, wax residues, and anything collected during harvesting are washed away while the oranges tumble gently across the rollers. By the time they leave the washing line, every orange has a clean surface, But the real transformation has not even started. Everything so far has simply prepared the fruit for the moment when machines finally reach the juice hidden inside. The cleaned oranges continue across inspection conveyors where cameras and optical sensors examine their size, color, and external condition. Mechanical diverters remove fruit that falls outside programmed limits, while the accepted oranges continue forward in an uninterrupted stream. At first glance, the line appears calm, but every conveyor is carefully synchronized because the extraction machines ahead work at remarkable speed. Hundreds of oranges every minute approach the point where peel, juice, pulp, and seeds will all separate into completely different production paths. Each orange enters an individual cup inside the extraction machine. Matching cups close around the fruit, holding it firmly without crushing it prematurely. A stainless steel tube pushes downward through the center, while pressure squeezes the orange between the supporting cups. Instead of simply cutting the fruit open, the system presses juice from the inside while keeping much of the bitter peel oils separated from the liquid. Juice, pulp, and fine fruit particles rush downward into collection channels, while peel sections follow an entirely different route. The extraction lasts only moments, yet in that brief instant, the whole orange becomes several individual material streams, each destined for a different purpose. The freshly extracted juice immediately passes through coarse screening systems designed to remove seeds, larger membrane fragments, and oversized pulp pieces. Stainless steel screens allow liquid and fine pulp to continue while larger solids remain behind. Pumps transfer the screen juice into enclosed pipelines before oxygen has much opportunity to affect freshness. The liquid still contains natural pulp, microscopic fruit particles, and dissolved fruit components that give orange juice its body and appearance. Meanwhile, the peel begins its own journey. Although no longer needed for bottled juice, the peel still contains valuable compounds. Mechanical presses recover peel oils from the outer rind before the remaining material moves toward other processing operations. Nothing about the orange simply disappears once extraction is complete. Every section of the fruit enters equipment specifically designed for that material. Back in the juice stream, another important separation takes place. Centrifugal equipment spins the liquid at high speed, allowing heavier pulp particles to separate from the thinner juice. Depending on the intended product style, processors can remove part of the pulp, retain all of it, or later blend controlled amounts back into the finished beverage. This flexibility allows one production line to create products ranging from pulp-free juice to varieties containing generous amounts of natural pulp. At this stage, the liquid finally resembles recognizable orange juice, yet several important transformations still remain. The juice moves toward deaeration equipment where dissolved oxygen is carefully reduced. Oxygen naturally enters during extraction as fruit breaks apart, but too much oxygen can gradually affect flavor quality over time. Inside enclosed vessels operating under controlled conditions, unwanted gases separate from the juice before it continues deeper into the factory. Now the process begins preparing the juice for long-term stability. The juice enters pasteurization through enclosed stainless steel pipelines connected to large plate heat exchangers. Heat transfers rapidly across thin metal plates, while carefully controlled temperatures raise the juice just enough to reduce unwanted microorganisms without unnecessary damage to flavor or color. The heating stage lasts only a short time before another section of the exchanger immediately begins cooling the juice again. This rapid transition preserves much of the fresh fruit character while creating a product suitable for refrigerated distribution. Although pasteurization appears simple from the outside, it represents one of the most carefully controlled stages in the entire factory. Temperature sensors monitor the liquid continuously, while automated valves ensure every portion receives the required treatment. If any section falls outside specification, control systems immediately divert it away from finished production until correct conditions return. The cooled juice now enters insulated storage tanks that rise several stories high. Slow-moving agitators keep the contents uniform without introducing unnecessary air. These tanks serve as temporary reservoirs between juice preparation and packaging, allowing downstream filling lines to operate continuously even while upstream extraction rates fluctuate. Level sensors constantly monitor every tank, automatically directing juice wherever production requires it. Some production schedules require blending before filling begins. Juice from different storage tanks may combine to achieve the desired balance of sweetness, acidity, aroma, and pulp level. Automated flow meters control each incoming stream, while mixing systems gently circulate the combined juice until every section of the tank matches the next. Even though the beverage comes directly from fruit, consistency across thousands of bottles depends on these carefully controlled blending operations. While juice waits inside storage, packaging materials begin their own journey through the factory. Plastic bottles often start as compact PET preforms that look nothing like finished beverage containers. These thick plastic tubes already contain the bottleneck and threaded opening, but lack the familiar body shape. Preforms travel into heating ovens where infrared lamps soften only the body section while leaving the neck rigid. Each preform rotates continuously to achieve even heating before moving toward the blow molding machine. Inside the blow molder, molds close tightly around each heated preform. A stretch rod pulls downward through the softened plastic while high-pressure compressed air expands it outward against the chilled mold walls. Within seconds, every contour appears. The base, shoulder, sidewall, grip panels, and label area. The newly formed bottle exits, lightweight yet strong enough to survive filling, transport, and handling. Before filling, every bottle passes through internal cleaning. Bottles invert, while filtered air or treated rinse water removes any particles that may have entered during handling. They drain immediately before returning upright and moving toward the filling system. Cartons follow an entirely different preparation path. Flat laminated carton material unwinds from large rolls before folding into rectangular tubes. Longitudinal seams seal continuously while sterile systems prepare the interior for juice filling. Every packaging format follows its own engineering approach, but each shares the same objective: protect the juice from contamination while preserving quality during storage. Fanta, grape syrup, is much stronger than the drink in the bottle. It carries sweetener, acid, grape flavor, color, and stabilizing ingredients in concentrated form. As it enters the blending chamber, flow meters measure every movement. The treated water line moves beside it. Control valves adjust both streams, so the finished beverage holds the same ratio from the first container to the last. Inside the blender, the purple syrup thins instantly. The liquid changes from dense concentrate into bright grape soda base. Its color remains strong, but the texture becomes lighter. The blend is not sparkling yet. It is flat, chilled, and ready for carbonation. Before the syrup reaches this point, it is built in the syrup room. Treated water is pumped into a stainless steel tank. The tank has a polished interior, a bottom outlet, and an agitator that turns at a controlled speed. Sweetener enters first. Granulated sugar may be dissolved into the water, or liquid sweetener may be metered directly into the tank. If sugar is used, the crystals fall into the moving water and disappear gradually. The liquid becomes heavier and clearer as the crystals dissolve. A recirculation pump can pull syrup from the bottom and return it near the top, helping the batch become uniform without leaving dense sweet spots inside the vessel. The sweetened base passes through fine filtration. This catches undissolved material before flavoring and color are added. A clean syrup is easier to pump, easier to meter, and less likely to disturb the filling system later. The grape flavor concentrate enters through a closed dosing line. It is not added by volume guesswork. It is pumped in at a measured rate. The agitator pulls the flavor into the sweet base, and the tank slowly changes character as the grape profile spreads through the syrup. The purple color system is added in the same controlled way. A small amount changes the entire tank. Dark ribbons appear briefly around the inlet before the mixer folds them into the batch. The syrup shifts into a uniform purple tone with no streaks or pale zones. Acid ingredients are dosed into the syrup to sharpen the fruit profile and balance the sweetness. They dissolve into the moving liquid and change the sensory structure of the drink, but the process remains mechanical. Tank, pump, meter, agitator, sample point, and transfer line. The finished Fanta grape syrup rests in a holding vessel. Slow agitation keeps it consistent. Temperature is controlled so viscosity stays predictable. A pump then sends it toward the proportioning skid, where it will be diluted into finished beverage. The clear water used for dilution has its own route through the plant. Incoming water passes through particulate filtration first. This removes suspended solids that could affect clarity or damage equipment. It then moves through activated carbon, where unwanted taste and odor compounds are reduced. Additional polishing stages may adjust the mineral balance and remove fine impurities. The treated water must be consistent because it forms most of the finished drink. Even a small change in water profile can affect flavor, carbonation behavior, and appearance. After treatment, the water flows into storage tanks. These tanks keep the water ready for syrup making and final blending. Level sensors monitor the supply. Pumps draw from the tanks as the production line demands more volume. From the proportioning skid, the flat Fanta grape beverage moves toward chilling. A plate heat exchanger lowers the temperature quickly. The liquid flows between thin stainless steel plates, while a cold medium flows on the opposite side. Heat transfers through the metal, and the drink leaves colder than it entered. Cold soda accepts carbon dioxide more efficiently than warm soda. It also foams less during filling. This matters because Fanta grape must hold carbonation while moving through pipes, valves, and containers at high speed. The chilled liquid may pass through a deaeration step. In this unit, unwanted dissolved air is pulled from the beverage. Reduced pressure or controlled gas contact helps tiny air bubbles leave the liquid. Removing air makes carbonation more precise and helps the grape drink retain a cleaner sparkle. The flat, chilled beverage enters the carbonator. Carbon dioxide flows in under pressure through diffusers or contact surfaces. The gas breaks into fine bubbles and dissolves into the liquid. The drink changes from still purple, soda base into carbonated Fanta grape. From this point, the beverage stays inside closed, pressurized stainless steel pipework. Sudden pressure loss would release foam, so the route to the filler is smooth, short, and carefully controlled. The purple liquid moves forward without open tanks or splashing. Containers are prepared at the same time. PET bottles often begin as preforms. A preform is a thick plastic tube with the neck already finished. Threads and the sealing surface are complete, but the body is still small and heavy. The preforms enter a heating oven and rotate as infrared lamps warm the plastic. Once heated, each preform enters a blow mold. The mold closes around it. A stretch rod pushes down through the center, while compressed air expands the softened plastic outward. The bottle body forms against the cold mold walls. The base, shoulders, label panel, and sidewalls appear in one fast expansion. The mold opens, and the empty bottle exits by its neck ring. Air conveyors move it forward. Because the bottle is light before filling, it can be carried by its neck while air jets push it along the rails. Cans follow a different path. Empty aluminum cans arrive already shaped and usually already printed. they are open at the top. Before filling, they pass through a rinser that inverts them, blows filtered air inside, and returns them upright. Glass bottles move through inspection before filling. Cameras and light beams check the mouth, base, sidewall, and interior. Any damaged or contaminated bottle is rejected before it reaches the drink. The carbonated Fanta grape enters the rotary filler. The filler contains many valves arranged around a circular bowl. Bottles or cans move into position through star wheels, each one timed to match a filling valve. For plastic bottles, the container seals against the valve. Pressure equalizes before liquid enters. This prevents the soda from foaming violently. Once balanced, the valve opens and purple carbonated soda flows into the bottle. Fine bubbles rise through the liquid as the level climbs. The valve closes at the programmed fill height. The headspace above the liquid is kept within a set range. The bottle leaves the filler and moves immediately to capping. Caps are fed from a hopper into an orienting bowl. Each cap turns into the correct position and travels down a chute toward the capping heads. The head places the cap onto the bottle and tightens it to a controlled torque. The tamper band locks below the neck ring. For cans, the filled container moves into a seamer. An aluminum lid is placed over the open top. The can and lid rotate together while seaming rolls fold the lid curl and can flange into a double seam. The seal traps the carbonation inside the can. Cherry Coca-Cola production begins when a cherry flavor stream is metered into a dark cola syrup base. The cherry component is powerful, so it enters through a controlled dosing line rather than as a large volume. A metering pump pushes it into a stainless steel tank where the cola syrup is already circulating. The agitator pulls the liquid inward, drives it downward, and folds the cherry stream through the dense syrup until the added flavor no longer exists as a separate layer. The cola syrup itself has been built before this point. Treated water enters a syrup tank first. It is not ordinary untreated water. It has already moved through filtration systems that remove suspended particles, activated carbon beds that reduce unwanted taste and odor, and polishing stages that stabilize clarity and mineral profile. A measured volume of this treated water is held inside the syrup vessel. Sweetener is added through a dosing system. In some plants, the sweetener enters as granulated sugar. In others, a liquid sweetener stream is used. The agitator keeps the water moving so the sweetener disperses quickly. If dry sugar is used, the crystals fall into the moving water and dissolve gradually. The liquid becomes heavier and glossier as the sugar disappears. Mild heat may help the dissolution process, but the syrup is not boiled. The purpose is to create a smooth, sweet base with no grit or undissolved particles. The sweet base passes through fine filtration. This removes any remaining solid material before flavor concentrate is added. Clean syrup protects the pumps, meters, proportioning valves, and filling heads later in the line. Cola concentrate then enters through a closed pipe. It brings the core cola flavor, caramel color, acidity structure, and formula components that define the base beverage. The syrup darkens almost instantly. The tank changes from a clear sweet solution into a deep brown concentrate. The agitator continues turning. Dark streaks vanish into the syrup. The mixture becomes uniform from the top surface to the outlet at the bottom of the tank. This syrup is still too strong to drink. It is a concentrated flavor and sweetener base designed for precise dilution later. The cherry flavor addition is integrated into this cola syrup system. It must not overpower the cola base or remain uneven in the batch. The mixing sequence creates a combined cola cherry syrup that carries both profiles in one concentrated stream. The finished syrup moves into a holding tank. The tank may use slow agitation to keep the syrup uniform. Sensors monitor level and temperature. From here, a sanitary pump sends syrup toward the proportioning system. A separate treated water stream leaves the storage tanks and travels toward the same proportioning unit. This water bypasses the syrup tank and remains clear until it reaches the blender. Both syrup and water pass through flow meters. The proportioner is the point where concentrated syrup becomes finished strength cherry Coca-Cola. One line carries the dark cola cherry syrup. The other carries treated water. Automatic valves make continuous adjustments so the blend ratio stays fixed, even if pressure changes inside either line. Inside the mixing chamber, the syrup and water combine. The syrup thins rapidly. The color remains deep, but the viscosity drops. The beverage now has its finished sweetness, acidity, cola flavor, cherry note, and caramel brown appearance. It is still flat. The flat drink moves through a chilling system. It passes through a plate heat exchanger made from thin stainless steel plates. A cold circulating medium flows on the other side of the plates and draws heat away from the beverage. The liquid temperature drops quickly while the product remains sealed inside the system. Cold liquid absorbs carbon dioxide more efficiently than warm liquid. It also foams less during filling. This matters because a carbonated cola must enter cans or bottles at high speed without overflowing or losing too much gas. The beverage may pass through a deaeration stage before carbonation. In a deaerator, reduced pressure pulls dissolved air out of the liquid. Tiny bubbles rise and separate from the stream. Removing unwanted air helps the drink accept carbon dioxide more cleanly. Carbon dioxide enters through regulated gas lines. The gas is filtered and pressure controlled before reaching the carbonator. Inside the carbonator, chilled cherry Coca-Cola meets carbon dioxide under pressure. The gas dissolves into the liquid rather than escaping as bubbles. The drink now has its sparkling bite. From this point onward, it stays inside closed pressurized stainless steel pipework. A sudden pressure drop would release foam and reduce carbonation, so the finished beverage flows directly toward the filling machine. While the liquid is prepared, containers move along their own factory path. For PET bottles, the process begins with preforms. A preform is a short, thick plastic tube with a finished neck. The threads, sealing surface, and tamper band support are already molded. The body still has to be stretched into a full bottle. Preforms enter a heating oven. Infrared lamps warm the plastic body while each preform rotates. Rotation keeps the heat even around the circumference. The neck area is kept cooler so the threads do not distort. A heated preform enters a blow mold. The mold closes around it. A stretch rod pushes downward through the center, pulling the softened plastic lengthwise. Compressed air then expands the plastic outward until it touches the chilled mold wall. The bottle shape appears instantly. The base forms into pressure supporting feet. The shoulders and label panel set into the plastic. The mold opens and the new bottle exits by its neck ring. The bottles move through air conveyors. They are light before filling, so streams of air push them forward while rails support them by the neck. They travel toward rinsing in single file rows. At the rinser, each bottle is gripped, inverted, and cleaned internally with filtered air or treated rinse water. It drains briefly, turns upright again, and moves toward the filler. Aluminum cans follow another route. They arrive already formed and printed, open at the top. The cans enter an air rinser, turn upside down, receive a blast of filtered air, and return upright before filling. Glass bottles arrive fully formed. They pass through inspection before filling. Cameras and light systems check the mouth, base, sidewall, and inside surface. Defective bottles are removed before they can reach the beverage. The carbonated cherry Coca-Cola reaches the rotary filler under pressure. The filler contains many valves arranged around a circular carousel. Containers enter through a star wheel that spaces them evenly beneath those valves. a bottle seals against its filling valve. Pressure inside the bottle is balanced with the filler before liquid enters. This prevents the carbonated drink from surging into foam. For cans, the filling system also controls flow carefully to limit turbulence. The valve opens. Dark, sparkling cherry Coca-Cola flows into the container in a smooth stream. In a clear bottle, the liquid rises from the base, carrying fine bubbles through the brown body of the drink. The fill level reaches the programmed height and the valve closes. The filled container moves immediately toward closure. Plastic bottles pass under capping heads. Caps are fed from a bulk hopper, sorted into the correct orientation, and delivered down a chute. Each capping head places a cap on the bottleneck and tightens it to a set torque. The tamper band locks below the neck ring. Cans move into a seamer. A thin aluminum lid is placed on each filled can. The can and lid rotate together while seaming rolls fold the lid curl and can flange into a tight double seam. The seal traps carbonation inside without glue. Glass bottles receive crown caps. A metal crown is positioned over the mouth and pressed down. The ridged skirt crimps under the glass bead, forming a gas-tight closure. Sealed containers move directly through inspection. Fill level sensors check the amount of liquid. Cameras inspect cap angle, tamper band position, lid seam, crown placement, bottle shape, and printed surfaces. Any container outside tolerance is rejected by an air jet or mechanical pusher. Bottles then move toward labeling. For roll-fed labels, printed film unwinds from a reel. Registration sensors locate the printed marks. A cutter separates each label, adhesive attaches the leading edge, and the bottle rotates as the film wraps around the body. The trailing edge is secured with another adhesive point. Rollers smooth the label around the bottle so it sits straight and tight. Cherry Coca-Cola labels identify the variant, while the liquid inside remains the same dark cola color. Shrink sleeve labels may use a different route. A printed sleeve drops loosely around the bottle. Heat then shrinks the sleeve tightly to the container contours. Glass bottles can receive glued paper labels pressed flat by brushes as the bottle turns. Cans usually carry their printed design before filling, so they move from seaming and inspection directly toward coating and packing. Pepsi cans lock shut under a double seaming head while the cola inside is still cold, pressurized, and fizzing against the lid. A filled aluminum can enters the seamer through a star wheel. The can body is open at the top, and the carbonated Pepsi sits just below the rim with a controlled headspace above it. A lid drops onto the can flange. The seaming chuck holds it in place. Rollers move in with precise pressure, curling the lid edge and can flange together into a tight double seam. The first roller forms the metal. The second roller compresses it. The seam becomes a folded mechanical lock that holds carbonation without glue. The can leaves the seamer sealed, rigid, and ready for inspection. Inside, dissolved carbon dioxide remains trapped under pressure. Before the can reaches the seamer, it is filled in a rotary pressure filler. Empty cans move into the filler after rinsing. They are spaced by star wheels and carried around a circular filling bowl. Each can rises under a valve. The valve controls liquid flow, so the carbonated drink enters quickly without excessive foam. The Pepsi stream is cold at this point. Cold liquid holds carbon dioxide more efficiently and behaves more calmly during filling. The dark cola enters the can in a controlled flow. The level rises with fine bubbles moving upward through the liquid. When the programmed fill height is reached, the valve closes and the can moves immediately toward the lid feeder. The filler must work with speed and restraint at the same time. Carbonated liquid wants to release gas when pressure changes. The filling valve shapes the flow to reduce splashing. The short transfer from filler to seamer prevents gas loss before closure. The carbonated beverage arrives at the filler through closed stainless steel pipework. The line remains pressurized and smooth. Sharp turns and sudden pressure drops are avoided. The liquid moves from the carbonator to the filling bowl without open exposure. Inside the carbonator, chilled flat Pepsi receives carbon dioxide. The liquid enters through a controlled feed line. Carbon dioxide enters under pressure through diffusers or contact surfaces. The gas breaks into fine bubbles and dissolves into the cola. The system controls pressure, liquid temperature, and gas flow, so every batch reaches the target carbonation level. The beverage is chilled before carbonation. It passes through a plate heat exchanger, where thin stainless steel plates separate the cola from a cold circulating fluid. Heat leaves the beverage rapidly. The liquid exits cold, dense, and ready to absorb gas. Some lines remove dissolved air before carbonation. In a deaeration unit, the flat drink moves under reduced pressure. Tiny air bubbles separate from the liquid and are pulled away. This makes carbonation more consistent and helps the drink hold its sparkle after sealing. The flat Pepsi comes from a blending system. Treated water and concentrated syrup meet at a proportioner. The syrup line is dark, sweet, and strong. The water line is clear and neutral. Flow meters measure both streams, and automatic valves adjust the ratio continuously. As the two streams combine, the syrup thins into finished strength cola. The color remains deep brown, but the flavor, sweetness, acidity, and body shift into the final beverage balance. This flat cola moves directly toward chilling, deaeration, and carbonation. The syrup is made in a separate syrup room. Treated water enters a stainless steel mixing tank. Sweetener is added first. It may arrive as liquid sweetener or as sugar dissolved into the water. The tank agitator keeps the base moving so no dense layer forms at the bottom. When sugar crystals are used, they fall into the water and gradually disappear. The mixture becomes heavier and glossy as the solids dissolve. Recirculation pumps may draw syrup from the bottom and return it near the top, creating a uniform sweet base. The sweet base passes through filtration before flavoring. Fine screens or filters remove undissolved material. Clean syrup protects proportioning valves, pumps, and filling equipment later in the process. Pepsi concentrate then enters through a closed dosing line. Caramel color spreads through the sweet base. Acids and flavor components blend into the liquid. The tank changes from clear syrup into a dark cola concentrate. The agitator turns steadily until the batch is uniform from the surface to the outlet. The finished syrup is much stronger than the drink itself. It is held in a tank with slow agitation. Pumps send it forward only as the proportioner requires it. The syrup flow and treated water flow create the finished cola continuously during production. The treated water begins as incoming plant water. It moves first through particulate filtration to remove suspended solids. It then passes through activated carbon, which reduces unwanted taste and odor. Additional polishing steps create a consistent water base for syrup making and final blending. This water matters because it makes up most of the beverage. Its clarity, taste, and mineral balance must stay steady. Sensors monitor flow, pressure, and treatment performance before the water enters storage tanks. While the liquid side is prepared, containers move through their own system. Aluminum cans arrive empty, lightweight, and open at the top. They are already formed and printed before entering the filling hall. The cans feed from depalletizers into single-file lanes. Air conveyors and guide rails control their movement without crushing the thin walls. Before filling, the cans are rinsed. They invert, receive a blast of filtered air or treated rinse water, drain, and return upright. This removes loose particles from the interior before the cola enters. PET bottles follow another route. They often begin as preforms. A preform is a short, thick plastic tube with a finished threaded neck. The body has not yet been expanded. The preforms enter a heating oven and rotate beneath infrared lamps so the plastic warms evenly. A heated preform enters a blow mold. The mold closes around it. A stretch rod pushes down through the center, pulling the softened plastic lengthwise. Compressed air then expands it outward until it touches the chilled mold walls. The base, shoulders, sidewall, and label panel form at once. The mold opens and the empty bottle exits by its neck ring. Air conveyors carry it forward. Because the bottle is light before filling, air jets can push it along while rails support the neck finish. The bottles pass through rinsing before filling. Each bottle is gripped, inverted, cleaned internally, drained, and returned upright. It then enters a pressure filler similar in purpose to the can filler, but matched to bottle geometry. For plastic bottles, the filling valve seals around the mouth. Pressure is balanced before liquid enters. Pepsi flows into the bottle with controlled turbulence. The fill level rises to the target height, and the valve closes. The filled bottle moves immediately to capping. Caps are sorted in an orienting bowl and sent down chutes to the capping heads. Each cap lands on the bottleneck and tightens to a controlled torque. The tamper band locks below the neck ring as the cap finishes turning. Glass bottles use a heavier container path. They pass through inspection before filling. Cameras and light systems check the mouth, base, sidewall, and interior. After filling, crown caps or threaded closures seal the bottle. The closure must hold carbonation pressure as the beverage warms and moves through packing. Every sealed container enters inspection. Fill level sensors check the liquid amount. Cameras inspect caps, can seams, bottle shapes, crown placement, dents, thread finish, and printed decoration. Any defective unit is removed automatically from the conveyor. Filled containers are often wet on the outside because the beverage is cold. Air knives remove condensation. Thin, high-speed sheets of air strike the cans and bottles from multiple angles. Droplets break away from lids, seams, shoulders, labels, and bases. 7-Up production begins with a clear, lemon-lime base that must stay bright, transparent, and free of visible particles from the first mixing stage. Treated water enters the blending room through closed stainless steel pipework. Before it reaches the tank, the water has already passed through filtration stages that remove suspended particles. Carbon treatment removes unwanted taste and odor. Final polishing creates a consistent liquid base that will not interfere with the clean lemon-lime flavor. The treated water collects in a sealed storage tank. Sensors measure level, temperature, and flow. A pump sends a controlled volume into the main dissolving vessel. The tank interior is smooth and polished, so the liquid can circulate without dead spots. The agitator begins turning before sweetener is added. Its blades pull the water downward and drive it outward in a steady loop. This motion prepares the tank for sugar, liquid sweetener, or another specified sweetening system. Sweetener enters through a dosing line. If granulated sugar is used, the crystals fall into the moving water and dissolve as the liquid rotates. If liquid sweetener is used, it flows in as a dense stream and blends into the water more quickly. The tank keeps the liquid moving until the base is uniform. The sweetened liquid remains clear. It does not darken like cola syrup or become opaque like some fruit-flavored drinks. The mixture becomes slightly heavier and glossier, but it must keep a clean appearance. The sweet base passes through fine filtration. Small undissolved particles are removed before the beverage reaches flavoring and carbonation equipment. This protects the later valves and meters, but it also helps preserve the transparent look of the finished drink. A lemon-lime flavor concentrate is prepared in a separate dosing system. It is strong, aromatic, and added in a small amount compared with the full batch volume. Metering pumps push it through a narrow stainless steel line into the moving sweet base. The concentrate disappears into the tank without changing the liquid into a dark or cloudy drink. The agitator folds the flavor through the full volume. Because 7-Up is a clear soda, the flavor components must disperse evenly and remain stable without visible separation. Acid ingredients are introduced next. They create the sharp citrus structure that balances the sweetness. The acid stream is metered into the tank below the surface, where the moving liquid immediately pulls it through the base. The liquid is mixed until sweetness, acidity, and flavor strength are consistent. The tank does not rely only on time. Flow meters, temperature readings, and recipe controls keep the batch inside its target range. At this stage, the beverage base is strong and still. It has lemon-lime flavor, sweetness, and acidity, but it may not yet be at final drinking strength. If the process uses a concentrated syrup system, the base moves to a proportioner. The proportioner receives 2 streams. One stream carries the strong lemon-lime syrup. The second stream carries treated water from storage. Each stream passes through a flow meter before blending. The machine constantly compares the 2 flows. If the water stream rises, the syrup stream adjusts. If syrup pressure shifts, the water valve corrects. This keeps the final ratio stable across thousands of bottles or cans. Inside the blending chamber, the syrup thins instantly. The drink reaches finish strength while remaining clear and flat. It has no sparkle yet. It is still a non-carbonated lemon-lime beverage at this point. The flat 7-Up moves into cooling equipment. It passes through a plate heat exchanger. The beverage travels through narrow channels between stainless steel plates. A chilled medium moves on the opposite side of those plates and pulls heat away. The temperature drops quickly. Cooling is essential because cold liquid absorbs carbon dioxide more efficiently. It also fills more cleanly later, with less foam and less gas loss. The beverage may pass through a deaeration vessel. Reduced pressure draws dissolved air out of the liquid. Tiny bubbles rise from the stream and separate before the drink continues. Removing excess air gives carbon dioxide more room to dissolve and helps the finished soda behave consistently. Carbon dioxide enters through regulated gas lines. The gas passes through pressure control equipment before reaching the carbonator. Inside the carbonator, cold 7-Up meets carbon dioxide under pressure. The gas dissolves into the liquid, forming the sharp, sparkling bite. The drink is now finished and carbonated. From this point onward, it stays in closed pressurized pipes. The system keeps the gas inside the liquid until the container is sealed. While the beverage is being prepared, empty containers are moving through their own lines. For plastic bottles, the process begins with PET preforms. These are short, thick plastic tubes with finished neck threads. The neck is already complete. The body is still compact and must be expanded into the final bottle shape. The preforms enter a heating oven. Infrared lamps warm the plastic body as each preform rotates. Rotation prevents one side from heating faster than the other. The neck area stays cooler, so the threads and sealing surface keep their exact dimensions. A heated preform moves into a blow mold. The mold closes around it. A stretch rod drives downward through the softened plastic, pulling it lengthwise. Compressed air then expands the plastic outward against the chilled mold wall. The bottle forms instantly. The base, shoulders, grip panels, and label area appear as the plastic presses into the mold. The mold opens, and the empty bottle exits by its neck ring. The bottles move through air conveyors toward rinsing. Because the bottles are very light before filling, they are supported by the neck rather than pushed heavily along the base. Airflow moves them forward in a controlled stream. At the rinser, each bottle is gripped, inverted, and cleaned internally with filtered air or treated rinse water. The bottle drains, rotates upright, and moves toward the filler. Can lines prepare a different container? Aluminum cans arrive already shaped and printed with open tops. They pass through an air rinser, turn upside down, receive a blast of filtered air. and return upright before filling. Glass bottle lines begin with formed bottles. Cameras and light systems inspect the mouth, base, sidewall, and interior. Any bottle with a crack, chip, or visible defect leaves the line before filling. The carbonated 7-Up arrives at the filling machine through pressurized piping. The filler is a rotary carousel with many filling valves arranged around a central bowl. Containers enter through a star wheel that spaces them precisely. Each bottle or can aligns under a filling valve. Because the drink is carbonated, the filling system controls pressure before liquid enters. The container is sealed against the valve, and internal pressure is balanced with the filler environment. The valve opens. Clear sparkling 7. Up flows into the container. In a transparent bottle, the liquid rises almost invisibly, except for the fine bubbles forming along the wall. The fill level reaches the programmed height, and the valve closes. The filled container moves immediately to sealing. Plastic bottles travel under capping heads. Caps arrive from a sorter in the correct orientation. Each head places one cap on the threaded neck and tightens it to a set torque. The tamper band locks below the neck ring. Cans move into a seamer. A thin aluminum lid is placed over the filled can. The can and lid rotate together while seaming rolls fold the lid curl around the can flange. A second roll compresses the folded metal into a tight double seam. Glass bottles receive crown caps. The capper presses a metal crown onto the mouth and crimps its edge beneath the glass bead. The closure traps carbonation inside the bottle. Sealed containers pass through inspection. Fill level sensors check the amount of liquid. Cameras examine caps, crowns, can seams, bottle shape, and printed surfaces. Low fills, high fills, crooked caps, weak seams, and damaged containers are rejected automatically. Bottles move toward labeling after inspection. Since 7-Up is clear, bottle and label alignment matter visually. The label must sit evenly around the container without covering the wrong panel or twisting across the body. For roll-fed labels, printed film unwinds from a reel. Registration sensors locate the print marks. A cutter separates each label. Adhesive attaches the leading edge to the bottle, and the bottle rotates as the film wraps around it. The trailing edge is sealed into place. Some formats use pressure-sensitive labels. These peel from a backing web and press onto the bottle through soft rollers. Glass bottles may receive glued paper labels that are brushed flat as the bottle turns. Cans usually arrive with their design already printed on the metal, so they move directly toward coating and packing after seaming and inspection. Coating equipment marks each container. Inkjet printers place production information onto the cap, bottle shoulder, label, can base, or glass surface. The code appears in a fraction of a second while the container remains in motion. Cold filling can create condensation on the outside. Air knives remove it. High-speed sheets of air strike the cap, shoulder, sidewall, seam, and base. Dry containers continue more reliably into packaging machinery. Poppy production begins with a sharp apple cider vinegar ingredient stream being measured into a much larger beverage base. The vinegar is not added loosely. It moves through a controlled dosing line with pumps measuring the amount before it enters the blending system. Because the flavor is strong and acidic, the dose must spread evenly through the full batch. The tank is already moving before the stream enters. Treated water is the main liquid. Incoming water passes through filtration to remove suspended particles. Carbon filtration reduces unwanted taste and odor. Final polishing stages create a clear, neutral base. This water is stored in sealed stainless steel tanks before blending. A measured quantity of treated water enters the main blend tank. The agitator starts turning below the surface. Its blades pull the water downward and push it outward along the tank wall. The movement creates a full tank circulation pattern, so later additions do not remain concentrated in one area. The apple cider vinegar stream enters beneath the surface. It folds into the moving water and quickly disperses. The acidity changes the base before sweetener or flavor is fully built. The liquid remains clear, but its sharp profile is now established. Sweetener is added next. Poppy-style drinks usually use a lighter sweetening system than a full sugar soda, so the sweetener amount is much smaller than in a traditional syrup room. The sweetener may enter as a liquid solution or as a prepared blend that dissolves quickly. The agitator continues moving. Sweetness spreads through the acidic water and softens the sharp edge of the vinegar. The base becomes balanced enough to carry fruit flavor, but it is still flat and uncarbonated. Prebiotic fiber ingredients are prepared carefully because they must dissolve cleanly and remain stable in the drink. A small preparation tank may receive treated water first. The fiber ingredient is added slowly while mixing prevents clumps. Once fully dispersed, this solution is pumped into the main blend. The fiber stream enters through a closed line. Flow meters confirm the addition. The main tank pulls the stream into circulation and spreads it through the beverage. The liquid must stay smooth, with no visible particles or thick sections. Acid balance is adjusted after the vinegar and fiber stream are in the tank. Fruit-flavored sparkling drinks need a controlled bright taste, not a harsh one. Additional acid or buffering ingredients can be metered in depending on the flavor. The tank mixes until the liquid reaches a uniform base condition. Flavor concentrate enters through another dosing line. Strawberry lemon, raspberry rose, orange, grape, cherry limeade, watermelon, or other varieties can be produced by changing the concentrate connected to the blending system. The concentrate is small in volume but strong in effect. The flavor stream hits the moving liquid and disappears. The tank turns the sharp, lightly sweetened base into a specific flavor profile. The mixture must be uniform before carbonation because once the drink is in pressurized piping, there is little opportunity for heavy correction. Color ingredients may be added depending on the variety. Some poppy drinks remain lightly tinted. Others take on a brighter fruit color. The color stream is metered in carefully. A very small amount changes the entire tank, so mixing continues until no streaks remain. The beverage base now contains treated water, vinegar, sweetener, fiber solution, acid balance, flavor, and color. It is still not finished. It must be clarified through filtration or strainers if the formula requires it, then chilled and carbonated. The liquid moves through a fine filtration stage. This step removes undissolved specks and protects later valves and filler nozzles. The drink must remain clean and smooth as it travels through high-speed equipment. The filtered base flows into a balance tank before final processing. Pumps pull from this tank and send the beverage toward cooling. Flow remains steady so the carbonation system receives an even supply. The drink enters a plate heat exchanger. It travels through narrow stainless steel passages. On the other side of the plates, a chilled medium removes heat. The beverage temperature drops quickly while the liquid remains sealed inside the system. Cold liquid absorbs carbon dioxide more efficiently than warm liquid. Cooling also reduces foam when the beverage enters cans. This is important because poppy is packaged as a sparkling drink, and uncontrolled foam would interfere with accurate fills. The chilled beverage may pass through a deaerator. Reduced pressure pulls dissolved air out of the liquid. Tiny bubbles rise and separate from the stream. Removing excess air helps the carbon dioxide dissolve more cleanly and keeps the drink's carbonation consistent. Carbon dioxide enters through regulated gas lines. Pressure control equipment stabilizes the gas before it reaches the carbonator. Inside the carbonator, chilled poppy meets carbon dioxide under pressure. The gas dissolves into the drink and creates the sparkling texture. From this point onward, the beverage stays inside pressurized stainless steel piping. The system keeps carbon dioxide dissolved until the can is sealed. The finished drink travels directly toward the filler. Empty aluminum cans move on a separate line. They arrive already formed, decorated, and open at the top. The cans are thin and lightweight, but they are designed to hold internal pressure once sealed. Guide rails organize the cans into single-file movement. The cans enter an air rinser. Curved tracks turn each can upside down. Filtered air blasts the inside, removing loose particles. The cans rotate upright again and continue toward filling. The rotary filler receives the cans through a star wheel. The star wheel spaces every can beneath a filling valve. Above the valves, the filler bowl holds chilled, carbonated poppy under controlled pressure. Each can reaches its valve. Pressure and flow are controlled so the drink enters smoothly. The valve opens and the sparkling liquid flows into the can. Foam is held low by the cold temperature and the controlled filling environment. The fill level rises quickly. When the target volume is reached, the valve closes. A small headspace remains at the top. This space allows the lid to be applied and the sealed can to hold carbonation properly. The filled can moves immediately to lid placement. Aluminum lids are fed from stacked magazines. A lid separator releases one lid at a time and places it over the open can. The can enters the seamer. The can body and lid rotate together. The first seaming roll curls the lid edge around the can flange. The second roll compresses the folded metal into a tight double seam. The seal is mechanical, created by folded aluminum rather than glue. The sealed can exits with the sparkling drink trapped inside. Inspection begins immediately. Fill level sensors check the amount of liquid. Cameras examine lid placement, printed surface condition, dents, and overall can shape. Seam inspection checks the closure profile. A defective can is rejected by an air jet or mechanical pusher. Accepted cans continue in a steady stream toward coating. An inkjet printer marks production information on the can base or another assigned location. The code is applied while the can moves at full speed. A vision system can verify that the code is present and readable. Fanta production begins with a small orange flavor stream entering a much larger sweet syrup base. The flavor concentrate is intense, so it is not added by sight or by guess. It moves through a closed stainless steel line, pushed by a metering pump that controls the dose. The syrup tank below it is already circulating. Its agitator pulls the liquid down through the center, throws it outward, and keeps the entire volume moving in a slow spiral. The sweet syrup starts with treated water. Before it reaches the tank, incoming water has already moved through filtration, activated carbon treatment, and polishing stages. Particles are removed. Unwanted taste and odor are reduced. The water becomes consistent enough to carry the same flavor strength in every batch. A measured volume of this treated water enters the syrup vessel. Sweetener follows through a dosing system. If dry sugar is used, the crystals fall into the moving water and dissolve gradually. If a liquid sweetener is used, it enters as a thicker stream and folds into the water as the agitator turns. The mixture becomes heavier as the sweetener dissolves. The surface changes from quick splashes to slower glossy waves. Controlled heat may help dissolve the sweetener completely. The liquid is not boiled. It is only warmed enough to form a smooth base with no gritty particles. The sweet base passes through fine filtration. Any undissolved material is caught before the syrup reaches the more sensitive mixing and filling equipment. Clean syrup protects pumps, flow meters, valves, and later filler nozzles. The filtered syrup enters the flavor building tank. This is where Fanta becomes different from a cola. Cola syrup is dark, caramel colored, and built around a compact, spice-like flavor system. Fanta syrup is bright, fruity, acidic, and usually designed around citrus character, color, and sometimes a slight clouded appearance. Orange flavor concentrate enters first or with the color system, depending on the formula. The stream is small, but it changes the whole tank. The syrup shifts from pale sweet liquid to a stronger orange base. The color looks deeper than the finished drink because dilution has not happened yet. Acid ingredients are added next. They create the sharp edge behind the sweetness. Citric acid is common in orange-flavored drinks because it gives a citrus-like bite. The acid is dissolved or added as a prepared solution. It enters below the surface and disappears into the moving syrup. Some orange soft drink formulas use an emulsion. Citrus oils do not naturally mix with water, so they are dispersed into extremely small droplets and held in suspension. This can give the drink a fuller, slightly cloudy look instead of perfect transparency. If an emulsion is part of the formula, mixing speed must be controlled carefully. The tank needs enough motion to distribute the droplets evenly, but not so much force that the droplet structure is damaged. The agitator works steadily, folding the syrup over itself without turning the vessel into violent foam. The finished syrup is now concentrated, orange, sweet, acidic, and strongly flavored. It is still not the final beverage. It is too dense and too powerful to drink. It must be diluted with treated water at a controlled ratio. The syrup flows toward the proportioning unit. A separate stream of treated water arrives from storage tanks. Both streams pass through flow meters. The proportioner compares them continuously and adjusts automatic valves in small movements. The machine keeps the blend ratio fixed. If syrup pressure changes, the valve corrects. If water flow increases, the syrup flow adjusts with it. The process prevents weak sections, overly strong sections, and color variation during a long production run. Inside the blending chamber, the concentrated syrup meets the water. The liquid becomes lighter and brighter. Its viscosity drops. The drink now has finished flavor strength, sweetness, color, and acidity. It is flat Fanta, not carbonated Fanta. The flat beverage moves into chilling equipment. It passes through a plate heat exchanger, flowing between thin stainless steel plates. A cold medium moves on the other side of the plates, pulling heat from the drink without mixing with it. The temperature drops quickly. Cold liquid absorbs carbon dioxide more easily than warm liquid. Cooling also prevents excessive foaming later, when the drink enters bottles or cans at high speed. The beverage may then pass through deaeration. In this stage, reduced pressure draws dissolved air out of the liquid. Tiny bubbles rise from the stream and separate. Removing excess air helps carbonation enter more cleanly and improves the way the drink behaves under pressure. Carbon dioxide enters through regulated gas lines. The gas is filtered and pressure controlled before it reaches the carbonator. Inside the carbonator, chilled Fanta and carbon dioxide meet under pressure. The gas dissolves into the liquid and creates the sparkling texture. From this point forward, the drink must remain enclosed. It travels through pressurized stainless steel, piping toward the filler. If the pressure dropped suddenly, carbon dioxide would escape as foam. While the beverage is being prepared, the containers are formed and cleaned. For PET bottles, production begins with preforms. A preform looks like a short, thick plastic tube with a finished threaded neck. The neck is already shaped with threads and a sealing surface. The body still needs to be expanded. Preforms enter an oven where infrared lamps heat the plastic. Each preform rotates while it moves through the oven, so the body warms evenly. The neck stays cooler because it must keep its exact dimensions for the cap. A heated preform enters a blow mold. The mold closes around it. A stretch rod pushes down through the center and pulls the plastic lengthwise. Compressed air then expands the softened plastic outward until it touches the chilled mold wall. The bottle shape appears instantly. The base forms into pressure-supporting feet. The shoulders curve outward. The label panel and grip contours set as the plastic cools against the mold. The mold opens and the empty bottle exits by its neck ring. The bottles travel through air conveyors toward rinsing. They are light and thin, so air pushes them forward while rails support them by the neck. At the rinser, each bottle is inverted and cleaned inside with filtered air or treated rinse water. It drains, turns upright, and moves toward the filler. Can lines follow a different route? Empty aluminum cans arrive open at the top. They are already formed and printed. They enter an air rinser, turn upside down, receive a blast of filtered air, and return upright before filling. Glass bottle lines use formed bottles that pass through camera inspection before rinsing. The equipment checks the mouth, base, sidewall, and inside surface. Only clean, intact bottles continue to the filler. The filler is a rotating carousel. Containers enter through a star wheel that spaces them exactly. Each bottle or can is guided beneath a filling valve connected to the pressurized Fanta supply. Because the beverage is carbonated, filling is pressure controlled. A bottle seals against the valve. Pressure inside the container is balanced before liquid flow begins. This prevents a sudden eruption of foam. The valve opens. Orange Fanta flows into the container in a controlled stream. In a clear bottle, the liquid rises brightly from the base, carrying fine bubbles through the orange body. The fill level reaches the target point and the valve closes. The filled container moves immediately to sealing. Plastic bottles pass under capping heads. Caps are sorted, oriented, and delivered down a chute. Each capping head picks up one cap, places it on the bottleneck, and tightens it to a set torque. The tamper band locks below the neck ring. Cans move to the seamer. A lid is placed on each filled can. Seaming rolls fold the lid curl and can flange together. The first operation hooks the metal. The second compresses it into a pressure-tight double seam. Celsius production begins with a small, concentrated solution that carries the drink's functional ingredients before the full beverage volume is created. A measured amount of treated water enters a stainless steel preparation tank. The tank is smaller than the final blending vessel because this stage is built for accurate dissolution rather than high volume dilution. The agitator starts first, pulling the water into a circular motion. Powdered and liquid ingredients can then enter without forming heavy pockets at the bottom. Caffeine is measured through a controlled dosing system. It may be added as part of a prepared ingredient blend or dissolved separately before entering the main preparation stream. The amount is small compared with the final drink volume, so the dosing equipment must be precise. The ingredient enters beneath the surface and disappears into the moving water. Vitamin ingredients follow through separate feed lines or prepared solution tanks. They are added in controlled amounts and mixed until the solution is uniform. The goal is a clear, even ingredient stream that can later be diluted across thousands of cans without variation. Other formula components enter in the same controlled way. Some arrive as liquids. Some are dissolved in small side tanks before being pumped forward. The preparation tank keeps the solution moving so every ingredient spreads through the water evenly. This concentrated functional solution then passes through filtration. Fine filters remove any undissolved specks before the stream reaches the main beverage blend. The liquid must remain smooth because particles can interfere with valves, meters, and filling equipment later in the process. While this solution is being prepared, the main water stream is also being conditioned. Incoming water passes through particle filtration to remove suspended material. Activated carbon removes unwanted taste and odor. Additional polishing equipment stabilizes clarity and mineral behavior. The treated water collects in sealed stainless steel tanks where sensors monitor temperature, level, and flow. A large blending tank receives the first measured charge of treated water. The agitator begins rotating slowly, then builds a steady circulation. The tank is polished inside, so the liquid moves smoothly with no rough surfaces or dead zones. Sweetener components are added according to the product formula. In Celsius, this may involve a low-calorie or sugar-free sweetening system rather than the heavy sugar syrup used in many traditional soft drinks. The sweetener stream is dosed carefully because small amounts can strongly affect the final taste. The sweetener dissolves into the treated water. The liquid stays light and clear. It does not become thick and syrupy like a full sugar cola base. The agitator keeps the mixture uniform, while sensors track the batch condition. Acid ingredients are added next. They create the sharp, bright structure that supports the flavor. A measured acid solution enters through a closed line. The moving water pulls it downward and spreads it through the full tank volume. Flavor concentrate follows. The specific variety determines the concentrate used. Citrus, berry, tropical fruit, peach, grape, watermelon, or other flavor systems can be connected to the same blending equipment. The concentrate enters in a small stream but changes the character of the entire tank. Color ingredients are added when the variety requires them. Some formulas remain nearly clear, while others receive a light tint. The color addition is tiny, but the mixing must be complete. A small streak in the tank would become an uneven product in the cans. The concentrated functional solution now enters the main blend. It is pumped from the preparation tank through filtered stainless steel lines. Flow meters verify the addition. The liquid joins the flavored, sweetened, acidified base and is folded through by the main agitator. The beverage is now close to finished, but it still needs final dilution control and carbonation. If the plant uses a concentrate and water system, the blend moves to a proportioning unit. One pipe carries the strong beverage base. Another pipe carries treated water. The proportioner measures both streams continuously. Automatic valves make constant corrections, so the finished drink remains at the target strength. The strong base thins into the final beverage as it meets the water inside a closed mixing chamber. The flat Celsius beverage then moves into cooling. It passes through a plate heat exchanger made of thin stainless steel plates. Cold fluid moves on the other side of the plates, pulling heat from the drink. The beverage temperature drops quickly without contacting outside air. Cooling prepares the drink for carbonation. Cold liquid absorbs carbon dioxide more efficiently. It also creates a calmer filling condition later. A warm carbonated beverage would foam too heavily when it entered the can. The chilled liquid may pass through a deaeration stage. Reduced pressure pulls dissolved air out of the beverage. Tiny bubbles rise and separate from the stream. This step improves carbonation behavior by reducing unwanted gas before carbon dioxide is added. Carbon dioxide enters through regulated gas lines. Pressure control equipment stabilizes the flow before it reaches the carbonator. Inside the carbonator, chilled Celsius meets carbon dioxide under pressure. The gas dissolves into the liquid, creating the sparkling texture of the finished drink. From this point onward, the beverage remains enclosed inside pressurized piping. The liquid is finished, carbonated, and ready for the canning line. Empty aluminum cans move through a separate preparation route. They arrive already formed and printed, open at the top. The cans are lightweight, thin-walled, and shaped to hold internal pressure after seaming. Guide rails arrange the cans into a steady single-file stream. The cans enter an air rinser, where curved rails invert them. Filtered air blasts the inside surface, removing loose particles. The cans rotate upright again and continue toward the filler. The rotary filler receives the cans through a star wheel. The star wheel spaces every can beneath a filling valve. Above the valves, the filler bowl holds chilled carbonated Celsius under controlled pressure. Each can aligns with its valve. The filling system controls pressure and flow so the beverage enters without excessive turbulence. The valve opens and the sparkling drink flows into the can. The liquid rises quickly while foam is kept low by cold temperature and controlled filling conditions. The valve closes at the target fill volume. A small headspace remains at the top of the can. This space is needed for proper sealing and pressure behavior after the lid is applied. The filled can moves immediately to lid placement. Aluminum lids feed from a stacked supply. A lid separator releases one lid at a time and positions it over the open can. The can then enters the seamer. The can body and lid rotate together while seaming rolls press the metal edges into shape. The first operation curls the lid edge around the can flange. The second operation compresses the folded metal into a tight double seam. This seam seals the carbonated drink inside without glue. The aluminum folds lock together mechanically, forming a pressure-tight closure. Sealed cans move directly into inspection. Fill level sensors verify the liquid amount. Cameras check lid placement, seam condition, printed surface quality, dents, and overall can shape. Any defective can is rejected from the conveyor by an air jet or mechanical pusher. Monster Energy production begins with a concentrated ingredient base being built in a stainless steel batching tank. The tank receives a small volume of treated water first. The agitator starts before the ingredient streams arrive. Its blades create a strong inward pull, drawing liquid down through the center and sending it outward along the curved tank wall. This movement prevents heavy powders or dense liquid concentrates from collecting in one place. The water used in the batch has already passed through the plant treatment system. Incoming water is filtered to remove suspended particles. Activated carbon removes unwanted odor and taste. Additional polishing stages make the water clear and consistent. The finished water is stored in closed tanks before being pumped to the blending room. The first base addition is usually the sweetener system. Sugar, glucose syrup, or another specified sweetener stream is measured into the moving water. If dry sugar is used, it falls through a controlled feeder and disappears into the rotating liquid. If liquid sweetener is used, it enters as a thicker stream and folds into the water as the agitator turns. The sweetened liquid becomes denser. The surface changes from fast ripples to slower, glossy movement. Temperature may be raised slightly to help the sweetener dissolve, but the liquid is not cooked. The goal is a clear, smooth base that can carry the rest of the formula without gritty particles. This sweet base passes through fine filtration. The filter removes any undissolved sugar or small particles before the liquid reaches the precision ingredient area. Clean flow is important because later equipment depends on accurate metering through valves, pumps, and flow sensors. The filtered base returns to the main blending vessel. Acid ingredients are added through a metered line. They create the sharp structure behind the sweetness. The acid stream is small compared with the full batch volume, so it must be spread evenly. The agitator keeps the liquid moving until the acidity is uniform throughout the tank. The energy ingredient blend is prepared next. Caffeine, taurine, B vitamin components, and other formula ingredients are measured in smaller preparation vessels. Some ingredients arrive as liquids. Others are dissolved into water first, so they can enter the main tank as controlled solutions. Each addition is pumped through closed stainless steel lines. Flow meters track the amount. The ingredient streams enter beneath the surface, where the moving liquid immediately pulls them through the batch. The tank must distribute them evenly because the finished drink is filled at very high speed, with no chance to correct uneven concentration later. Flavor concentrate is then introduced. Monster varieties use different flavor systems depending on the product, so the same blending equipment can produce different versions by changing the programmed concentrate, color, and ingredient sequence. The concentrate enters in a small, powerful stream. The tank darkens, brightens, or shifts color depending on the variety. Color is metered separately when required. A small amount spreads through the entire batch and changes the appearance of the liquid. Greenish, golden, orange, blue, purple, or near clear varieties can be produced by changing this stream and the flavor system connected to it. The concentrated base is now strong, sweet, acidic, flavored, and loaded with dissolved ingredients. It is not yet the final beverage. It may be too concentrated for direct filling, so it moves toward a proportioning system where it will be diluted to finish strength. A second stream of treated water arrives from storage tanks. This water bypasses the small concentrate tank and moves directly toward the final blender. Flow meters measure both streams. One meter reads the concentrate flow, another reads the treated water flow. The proportioner adjusts both streams continuously. Automatic valves make small corrections whenever pressure or flow changes. The machine keeps the ratio locked so the drink has the same flavor strength, sweetness, acidity, and dissolved ingredient level from the first can to the last. Inside the final blending chamber, the concentrate and water combine. The intense base thins instantly. The drink reaches its final formula strength. At this stage, it is flat Monster Energy. It has color, sweetness, acidity, flavor, and dissolved energy ingredients, but it has no carbonation. The flat beverage flows into a cooling section. It passes through a plate heat exchanger, moving through narrow channels between stainless steel plates. Chilled fluid travels on the opposite side of the plates and pulls heat out of the drink. The beverage temperature drops quickly while the liquid remains sealed from outside air. Cooling prepares the drink for carbonation. Cold liquid absorbs carbon dioxide more effectively than warm liquid. Cold filling also helps reduce foam when the beverage enters the can. Before carbon dioxide is added, the beverage can pass through a deaerator. Reduced pressure pulls dissolved air out of the liquid. Tiny bubbles rise and separate from the stream. Removing excess air allows carbonation to behave more predictably and helps the drink stay consistent inside the sealed can. Carbon dioxide enters through pressure-regulated gas lines. The gas is filtered and controlled before reaching the carbonator. Inside the carbonator, chilled Monster Energy flows under pressure while carbon dioxide dissolves into it. The liquid becomes sparkling, but the gas remains trapped in solution because the system stays sealed and pressurized. From this point forward, the beverage must stay under controlled pressure. It moves through closed stainless steel piping toward the filler. Any sudden pressure drop would cause foaming and carbonation loss. While the drink is being blended and carbonated, empty cans move on a separate line. The aluminum cans arrive already formed, decorated, and open at the top. They are light, thin, and designed to hold internal pressure once sealed. The cans enter a lane-guided conveyor and move toward the rinser. Curved tracks invert each can. Filtered air blasts the interior to remove loose particles. The cans rotate upright again and continue toward the filling machine. They move in tight rows, with rails keeping them stable as they approach the star wheel. The rotary filler receives the cans one by one. The star wheel spaces them evenly and positions each can beneath a filling valve. Above the valves, the filler bowl contains chilled carbonated Monster under controlled pressure. The filling valve opens. The drink flows smoothly into the can. The liquid must enter without excessive turbulence. If it splashes too hard, foam rises and interferes with the fill level. The cold temperature and controlled pressure keep the fill clean. The can fills rapidly. A small headspace remains at the top. This space is necessary for proper sealing and pressure behavior after the lid is applied. The valve closes at the exact target volume, and the can moves immediately towards seaming. Aluminum lids feed from a stacked supply. The lid dispenser separates one end at a time and places it over each filled can. The can cannot remain open for long because carbonation would begin escaping. The seamer closes the package mechanically. The can body and lid rotate together. The first seaming roll curls the lid edge around the can flange. The second roll compresses the metal folds into a tight double seam. No glue is used. The pressure-tight seal is created by folded aluminum. The sealed cans travel directly into inspection. Fill level sensors verify the liquid amount. Cameras check the lid, sidewall, top surface, and printed body. Seam inspection systems examine the double seam. A can with a dent, low fill, high fill, weak seam, or missing code is rejected from the line. The accepted cans pass through a coding station. An inkjet printer marks the can with production information. The code is applied to the base or another assigned area while the can moves at full conveyor speed. Because the drink was chilled before filling, condensation can form on the can surface. Air knives blast narrow sheets of high-speed air across the lid, sidewall, and base. Water droplets break away so the cans enter, packaging dry. The dry cans move into lane dividers. Guide rails split the flow into parallel rows. Timing screws control spacing. Stop gates and collators gather cans into the correct pattern for secondary packaging. Red Bull production begins with water being prepared before any flavor, sweetness, carbonation, or can ever enters the process. Incoming water first moves through a treatment system. It passes through filters that remove suspended particles. Activated carbon removes unwanted taste and odor. Additional polishing stages bring the water to a consistent clarity and mineral condition. The goal is a clean, neutral liquid that behaves the same way in every batch. The treated water flows into stainless steel holding tanks. These tanks are sealed and fitted with sensors that track level, temperature, and flow. Pumps draw water from the tanks and send it toward the blending area through closed sanitary pipework. A measured volume of treated water enters the first blending vessel. The agitator starts turning before the dry ingredients arrive. Its blades pull the water downward, push it outward along the tank wall, and create a steady circular movement through the entire vessel. Sugar is added into this moving water through a controlled dosing system. The crystals fall into the rotating liquid and begin dissolving. At first, the mixture looks slightly uneven. As agitation continues, the sugar disappears completely and the liquid becomes heavier, smoother, and more reflective. The sugar solution may be warmed slightly to speed dissolution. The heat is controlled because the drink must remain stable for later ingredient additions. The tank does not cook the liquid. It simply creates a smooth, sweet base with no gritty particles remaining. This sweetened base passes through fine filtration. Any undissolved material is removed before the liquid reaches the next blending stages. Clean filtration protects pumps, valves, meters, and filling equipment from blockage or uneven flow. The filtered liquid returns to the main blending line. Acid ingredients are prepared in a separate solution and metered into the moving stream. These acids give the drink its sharp, bright structure. The addition is small, but it affects the entire taste balance of the beverage. The agitator folds the acid solution through the sweet base. The liquid remains pale and clear. Unlike cola, there is no dark caramel color. Every ingredient must dissolve neatly because the finished drink has a light, translucent appearance. The functional ingredient stream is prepared next. Caffeine, taurine, vitamin components, and other formula ingredients are measured in controlled amounts. Some are added as ready-made liquid solutions. Others are dissolved in smaller preparation tanks before being pumped into the main blend. These ingredients enter through narrow stainless steel lines. Flow meters and dosing pumps control their addition. The amounts are precise because a small dosing error would affect a large volume of drink. Once added, the main agitator and inline mixers spread them evenly through the batch. Flavor concentrate is introduced after the base ingredients are dissolved. It enters as a small but powerful stream. The flavor must spread through the full tank without forming strong pockets. The mixing system keeps the liquid moving until the entire batch carries the same flavor intensity. If a colored Red Bull variety is being produced, color is added through another metered stream. A small amount changes the appearance of the whole tank. The color disperses until the liquid is uniform from the top surface to the bottom outlet. The beverage base is now sweetened, acidified, flavored, and fortified with its dissolved ingredients. It is still not finished. It has no carbonation, and its temperature is not yet ideal for filling. The blended liquid moves toward a proportioning system if the process uses a concentrated base. One pipe carries the strong blend. Another pipe carries treated water. Flow meters monitor both streams continuously. Automatic valves adjust the ratio so the final drink strength stays constant. Inside the mixing chamber, the concentrated base and treated water combine. The drink reaches its final dissolved ingredient level. It is now the correct flavor, sweetness, acidity, and appearance, but it is still flat. The flat beverage enters a heat exchanger. It flows through narrow channels inside stainless steel plates. On the other side of those plates, chilled liquid removes heat. The drink cools quickly while remaining sealed from outside air. Cold liquid absorbs carbon dioxide more efficiently than warm liquid. Cooling also prevents excessive foam during filling. If the beverage were too warm, gas would escape too easily when it entered the can. The chilled drink may pass through a deaeration vessel. Reduced pressure pulls dissolved air out of the liquid. Tiny bubbles rise and separate from the stream. Removing excess air helps the carbon dioxide dissolve more cleanly and gives the beverage more stable carbonation behavior. Carbon dioxide enters through regulated gas lines. The gas passes through pressure control equipment before reaching the carbonator. Inside the carbonator, chilled Red Bull meets carbon dioxide under pressure. The gas dissolves into the liquid, creating the sharp, sparkling texture of the finished drink. From this stage onward, the beverage stays inside closed pressurized pipes. It cannot be exposed to open air or low pressure before filling, because carbonation would escape as foam. While the drink is being made, empty aluminum cans are prepared on another line. The cans arrive already formed and printed with open tops. They are light, thin-walled, and designed to hold internal pressure after sealing. Guide rails organize them into single-file streams. The cans enter an air rinser. Curved rails invert each can. Filtered air blasts the interior to remove loose particles. The cans drain or clear, then turn upright again and continue toward the filler. The filler is a large rotary machine with many filling valves. Carbonated Red Bull enters the filler bowl under pressure. Empty cans arrive through a star wheel that spaces them perfectly beneath the valves. Each can moves into position. The filling system controls pressure and flow, so the carbonated beverage enters smoothly. The valve opens, and pale sparkling liquid drops into the can in a controlled stream. Foam is minimized by the cold temperature and pressure-balanced filling conditions. The liquid rises quickly inside the can. When the correct volume is reached, the valve closes. A small headspace remains at the top so the can can be sealed properly and hold internal pressure. The filled can moves immediately to the lid applicator. Thin aluminum lids are fed from a stacked supply and placed one by one over the open cans. The lid must arrive immediately after filling, so carbonation stays inside the package. The can enters the seaming machine. The can body and lid rotate together, while seaming rolls press the metal edges into shape. The first operation curls the lid edge around the can flange. The second operation compresses the folded metal into a tight double seam. This seam is the pressure-tight closure. It contains the carbonated drink without glue or heat sealing. The finished can leaves the seamer sealed and ready for inspection. Sensors check the fill level. Cameras inspect the lid, seam position, printed can surface, and overall shape. Seam inspection systems verify that the closure is properly formed. Any can outside tolerance is removed from the line by a fast reject mechanism. The accepted cans pass through a coding station. An inkjet printer marks production information on the base or another assigned area. The mark is applied while the can continues moving at high speed. Because the drink was chilled before filling, moisture may form on the can surface. Air knives blast thin sheets of high-speed air across the metal. Droplets are stripped from the lid, sidewall, and base. The cans must be dry before secondary packaging. The dry cans enter lane-dividing conveyors. Guide rails separate the flow into parallel rows. Timing screws and gates control spacing. Collators gather the cans into exact groups for multi-packs, trays, or cartons. For shrink-wrapped packs, plastic film feeds around each grouped set of cans. The loose bundle enters a heat tunnel. Hot air shrinks the film tightly around the can walls and pack corners. The film cools into a firm wrap that holds the cans together. For tray packs, a corrugated blank slides under the can group. Folding guides raise the sides around the base. The tray supports the cans from below. Film may then wrap around both tray and cans to create a stronger pack. For cartons, paperboard blanks feed from a magazine and fold around the grouped cans. Glue is applied to the flaps. Compression belts press the board together until the carton holds its shape. Finished packs move through inspection. Sensors check pack count, film position, carton closure, tray alignment, and code presence. Defective packs are diverted before palletizing. The accepted packs travel to the palletizer. Conveyors rotate selected packs, so each layer forms a stable pattern. A layer table gathers one full arrangement, squares the edges, and transfers it onto a pallet. Layer after layer builds upward. Each level is placed in a programmed pattern so the stack remains stable. Slip sheets may be added between layers when needed to improve load strength. Sprite is manufactured by preparing a citrus flavor syrup, blending it with treated water at a fixed ratio, carbonating the beverage to a precise dissolved CO2 level, then filling and sealing containers under counter. Pressure, so carbonation and aroma stay stable. Production starts with water because water chemistry controls acidity perception and carbonation behavior. Incoming water is filtered to remove suspended solids and then polished through fine filtration. Mineral content is adjusted to a target hardness and alkalinity so the final drink has consistent bite. Water is then cooled because colder water holds CO more efficiently and reduces foaming during filling. A sweetener stream is prepared in parallel. For sugar-based production, granulated sugar is dissolved in heated tanks with agitation until the syrup is clear. Syrup concentration is measured by density and held in a narrow band because it determines final sweetness after dilution. The syrup is filtered to remove undissolved crystals that could seed crystallization or clog valves. For other sweetener systems, a concentrated solution is prepared and handled as a metered liquid feed with consistent density. The citrus flavor system is built as a concentrate that can be dosed precisely. Lemon and lime flavor components often include oil-based fractions that must be emulsified to remain stable in water. The flavor concentrate is mixed in a blending tank where carriers and emulsifiers are combined with flavor oils. High shear mixing reduces oil droplet size and stabilizes the emulsion. Droplet size control prevents separation and reduces ring formation at the surface of the final beverage. The concentrate is filtered to remove any particulate and to protect dosing pumps. Acid addition is managed as part of syrup formulation because pH defines freshness and also affects how sweetener is perceived. Acid is prepared as a liquid solution for accurate dosing. It is injected into the syrup or into the flavor concentrate depending on process layout. pH is measured and adjusted to a tight set point. Small changes in pH shift the balance between sharp citrus and sweetness. Buffer salts can be used in very small amounts to reduce drift, but the main control is acid dose. If the formulation includes a clouding system to support the citrus profile, it is prepared as an emulsion stream. Cloud systems are designed to keep a slight visual opalescence and to carry flavor. They are mixed under shear and then held with gentle agitation so they do not cream. Stability is verified by checking droplet size and separation rate. Once sweetener syrup, flavor concentrate, acid, and any cloud system are ready, they are combined into a finished syrup. The syrup is mixed with controlled agitation that avoids foaming. The syrup is then held at a stable temperature and delivered to the proportioning blender through metered pumps. Filters at this stage protect the blender and carbonator from particles and gel lumps. Final beverage blending is done with a proportioning system that meters syrup and chilled treated water. The ratio is controlled by mass flow meters or by volumetric meters with density compensation. Ratio accuracy is the main determinant of consistent taste. The blended stream is monitored by inline soluble solids measurement. When solids drift, the control system adjusts valve positions to correct the syrup-water ratio. Before carbonation, the blended beverage is commonly deaerated. Deaeration removes dissolved oxygen and entrained air. Oxygen dulls citrus aroma over time and increases oxidation in flavor components. Air also reduces carbonation efficiency because it occupies headspace in the carbonator and promotes foam. Deaeration is performed under vacuum where the beverage spreads as a thin film. Vacuum pulls gases out and the liquid leaves with lower oxygen content. Carbonation follows, and it is controlled by temperature, pressure, and contact efficiency. CO2 supply is filtered and regulated to stable pressure. The cold beverage enters a carbonator, where CO2 is injected and dissolved under pressure. Many carbonators use a sintered stone or injector that forms fine bubbles. Fine bubbles create high surface area and dissolve quickly. The carbonator maintains a pressure high enough to keep CO2 in solution and prevent breakout. Dissolved CO2 level is monitored continuously. Instruments measure or infer carbonation based on temperature and pressure. The line targets a defined carbonation level that gives a crisp bite. If temperature rises, CO2 solubility drops and gas begins to break out. The system compensates by increasing pressure or improving cooling. Tight temperature control in the blending and carbonator sections therefore supports stable carbonation. Once carbonated, the beverage must be handled with low turbulence. High shear pumps and sharp piping bends can release CO2 and create foam. The line uses low shear pumps and smooth piping layouts. The product is kept under pressure all the way to the filler bowl. Pressure maintenance prevents CO2 loss and reduces foaming at the fill valve. Container handling runs in parallel with beverage. Preparation. Cans or bottles are conveyed, oriented, and cleaned. Cans are often rinsed and drained before filling. Bottles are oriented and may be rinsed or air blown to remove dust. Plastic bottles may be supplied from blow molding and then transferred to the filler quickly. Container temperature can influence fill behavior because warm containers promote foaming. Lines manage container staging to avoid excessive warming. Filling is performed on counter-pressure fillers. The container is first sealed to the fill valve and pressurized with CO2 to match filler bowl pressure. This equalization reduces foaming when liquid enters. The fill valve opens and beverage flows in at a controlled rate. Fill level is controlled by a probe or by timed flow depending on equipment design. Controlled flow reduces turbulence and helps maintain carbonation. After the container reaches fill level, the valve closes and pressure is released in a controlled way. Controlled release prevents the liquid from erupting and prevents excessive foam that could contaminate the seal. For cans, the lid is applied and the can is seamed immediately. For bottles, the The cap is applied immediately with controlled torque. Rapid sealing locks carbonation and reduces oxygen pickup. Headspace control is part of maintaining carbonation and flavor. The fill is set to leave a defined headspace volume. Many lines apply a CO2 jet just before capping or seaming. This displaces air from the headspace and reduces oxygen content. Reduced oxygen protects citrus aroma and reduces flavor drift. Headspace CO2 also supports equilibrium carbonation by providing a gas reservoir above the liquid. After sealing containers, move to inspection. Fill level inspection checks for underfills and overfills. Cap inspection checks for missing caps and skewed caps. Seam inspection checks seam thickness and overlap on cans. Leak detection can identify micro leaks that would cause carbonation loss. Out of specification units are rejected automatically. If the product is packed into multi-packs, the sealed units are collated next. Cans can be wrapped in film or placed in cartons. Bottles can be grouped in shrink packs or tray packs. Shrink film is applied and then heated to conform around the pack. Heating is controlled so it shrinks film without overheating the beverage. Cartoning systems erect cartons and load units with gating systems that maintain spacing. Canada Dry Ginger Ale is manufactured by preparing a ginger citrus flavor syrup, blending it with treated chilled water at a fixed ratio, carbonating the beverage to a controlled dissolved CO2 level, then filling and sealing containers under counter pressure so carbonation and aroma remain stable. Production starts with water because it defines the baseline taste and the way carbonation behaves. Incoming water is filtered to remove suspended solids and then polished through fine filtration. Mineral content is adjusted to a target profile because hardness and alkalinity change perceived sharpness and sweetness. Water is then cooled because colder liquid absorbs CO more efficiently and reduces foaming at the filler. A sweetener stream is prepared in parallel. For sugar-based production, granulated sugar is dissolved in heated tanks with agitation until the syrup becomes clear. Syrup concentration is monitored by density because it determines final sweetness after dilution. The syrup is filtered to remove undissolved crystals that could clog valves and create settling. For alternative sweetener systems, a concentrated sweetener solution is prepared and handled as a metered liquid feed with stable density. The ginger flavor system is built as a concentrate that can be dosed precisely. Ginger character often includes both water-soluble notes and oil-based notes that need controlled dispersion. Flavor components are staged in small tanks and metered by weight into a blending vessel. Oil-based fractions are emulsified so they remain stable in the final beverage and do not separate in storage. High shear mixing reduces oil droplet size and improves emulsion stability. The concentrate is filtered to remove any particulate that could seed haze or block nozzles. Acid addition is managed as part of syrup formulation because pH controls brightness and stability. Acid is prepared as a liquid solution for accurate metering. It is injected into the syrup blend or into the flavor concentrate depending on line design. pH is measured and trimmed to a tight set point because small shifts change the ginger bite and the perceived sweetness. Buffer salts can be used in very small amounts to reduce drift, but the main lever is acid dose. If the formula uses a color system or a cloud system, those are handled as separate dosing streams. Color is held in tanks with gentle mixing and metered into the syrup at a controlled rate. Cloud systems are prepared as emulsions that remain suspended and carry aroma. Cloud emulsion. Stability is controlled by droplet size and by the choice of emulsifier. These streams are filtered and then injected into the syrup blend under controlled mixing. Once sweetener syrup and flavor concentrate and acid and any supporting streams are ready, they are combined into a finished syrup. Mixing is designed to create uniformity without entraining air. Air entrainment creates foam and reduces carbonation efficiency later. The finished syrup is held at a stable temperature to keep viscosity consistent for metering. It is delivered to the proportioning blender through metered pumps and protected by final inline filters. Final beverage blending is done with a proportioning system that meters syrup and chilled treated water. Control can be mass flow based or volumetric with density compensation. Ratio accuracy is the main determinant of consistent taste from run to run. The blended stream is monitored by inline soluble solids measurement as a proxy for syrup ratio. When solids drift, the control system adjusts valves to correct the ratio in real time. Before carbonation, the blended beverage is typically deaerated. Deaeration removes dissolved oxygen and entrained air. Oxygen can dull delicate ginger notes over time and can change aroma character during storage. Air also interferes with carbonation by promoting foam and reducing CO2 dissolution efficiency. Deaeration is performed under vacuum, where the liquid spreads as a thin film. Vacuum pulls gases out and the liquid exits with lower oxygen content. Carbonation follows deaeration and is controlled by temperature and pressure and contact efficiency. CO2 supply is filtered and regulated to stable pressure. The cold beverage enters a carbonator where CO2 is injected under pressure. Injection often uses a sintered stone or fine bubble injector to create small bubbles with high surface area. High surface area improves dissolution speed and reduces large bubble breakout. The carbonator maintains pressure high, enough to keep CO2 in solution. Dissolved CO2 is monitored continuously by instrumentation or by calculation from pressure and temperature. Temperature is a critical variable because CO2 solubility drops as temperature rises. The system compensates for temperature drift by adjusting pressure and by tightening cooling upstream. Stable chilling of water and blended beverage is therefore essential for consistent carbonation. Once carbonated, the beverage must be transported with minimal turbulence. Turbulence releases CO2 and creates foam, which leads to fill problems and carbonation loss. The line uses low shear pumps and smooth piping layouts. Sharp bends and sudden diameter changes are avoided. The product remains under pressure from carbonator through filler bowl to keep gas dissolved. Container handling runs in parallel with beverage preparation. Cans or bottles are conveyed and oriented and cleaned. Cans are typically rinsed and drained before entering the filler. Bottles are oriented and can be air rinsed or lightly rinsed, depending on line design. Plastic bottles may be supplied from blow molding and transferred quickly to avoid dust pickup. Container temperature matters because warm containers promote foaming. Staging is designed so containers do not heat excessively before filling. Filling uses counter-pressure equipment designed for carbonated beverages. Each container seals to a fill valve and is pressurized with CO2 to match the filler bowl pressure. Pressure equalization reduces turbulence when liquid enters. The fill valve opens and beverage flows in at a controlled rate. Fill level is controlled by a level probe or by timed flow depending on the filler type. Smooth flow is critical because foaming can cause underfills and messy seals. After the target fill level is reached, the valve closes and pressure is released in a controlled way. Controlled release prevents eruption and reduces foam at the top. Cans are then lidded and seamed immediately. Seam rollers form a tight double seam that locks the lid to the can body. Seam geometry is controlled by roller profiles and force because seam, overlap, and tightness determine leak resistance. Bottles are capped immediately with controlled torque. Torque control ensures sealing without damaging threads or liners. Headspace control supports carbonation retention and aroma stability. A defined headspace volume is left above the liquid. Many lines apply a CO2 jet just before sealing. This displaces air in the headspace and reduces oxygen pickup. Reduced oxygen helps keep the ginger aroma crisp during storage. Headspace CO2 also supports equilibrium between dissolved CO2 and gas phase CO2. Immediately after sealing containers, move through inspection. Fill level inspection checks for underfill and overfill. Closure inspection checks for missing caps or misapplied lids. Seam inspection on cans can include overlap checks and thickness checks. Leak detection can see identify microleaks by pressure decay or vacuum methods. Out of tolerance units are rejected automatically to protect product consistency. If the product is produced in multiple packaging formats, the downstream handling changes slightly, but the goals remain the same. For multi-packs, cans are collated and wrapped in film or loaded into cartons. Bottles can be arranged into shrink packs or tray packs. Shrink film is applied and then heated to conform around the pack. Heat application is controlled so the film shrinks without overheating the beverage and driving CO2 loss. Cartons are erected and loaded with gating systems that maintain spacing and prevent scuffing. It all starts with malted barley, the soul of the beer. In a factory setting, the malt arrives by truckloads or freight trains already malted at a dedicated malting facility. Malting is a process in itself. Barley is soaked, allowed to germinate just enough to activate enzymes, and then dried and kilned to stop the growth. This controlled germination unlocks starches and enzymes that will later convert to fermentable sugars. The exact roast of the malt, pale, caramel, a chocolate, black, determines much of the final beer's color and flavor. For large-scale beers, base malts are used, usually lightly kilned, with small amounts of specialty malts blended in. The malt is piped into massive silos at the brewery, where it's stored dry and clean. When brewing begins, the malt is sent through a series of conveyors or airlifts to the mill. Here, roller mills crush the grain, not into flour, but into coarse grist. The idea is to crack the husk while leaving the interior accessible. Too fine, and the mash will become sticky and hard to filter. Too coarse, and sugar extraction drops. The grist is collected and weighed, then transported directly to the mash tun where the real transformation begins. In the mash tun, often a stainless steel vat the size of a swimming pool, the grist is mixed with hot water to form a thick porridge-like slurry. This step, called mashing, activates enzymes like amylase, which convert starches into simple sugars. The temperature is held precisely, usually around 65 and 68 degrees Celsius, depending on the style of beer. Too hot and the enzymes are denatured. Too cold and the starches won't fully convert. The mash is gently stirred using mechanical arms to ensure uniformity. For the next hour or so, the grain slowly transforms into a sweet liquid known as wort. When conversion is complete, the mash is transferred to the lautering vessel, sometimes built into the same tank. Lautering is the process of separating the liquid wort from the spent grain. A false bottom or fine slotted plates allow the liquid to drain through, while the grain bed itself acts as a natural filter. More hot water, known as sparge water, is sprayed over the top to rinse out every last bit of sugar. The collected wort flows to the brew kettle, while the spent grain, now protein-rich but sugar-poor, is conveyed out of the system. Many large breweries donate or sell this grain to farms as cattle feed. Next is the boil. In towering stainless steel kettles, the wort is brought to a rolling boil and held there for 60 to 90 minutes. This step sterilizes the liquid, halts enzymatic activity, and causes unwanted proteins to coagulate and fall out of suspension. It's also when hops are added. Hops are the cone-shaped flowers of the Humulus lupulus plant, prized for their bitterness, flavor, and aromatic oils. In a factory setting, hops usually arrive as compressed pellets for consistency. Early additions bring bitterness. Late additions and whirlpool hops contribute aroma and flavor. Boiling is carefully managed. A powerful steam jacket heats the vessel, while a system of condensers captures volatile compounds and steam vapor to reduce environmental impact. The smell during this stage is unmistakable. Sharp, herbal, sweet, and slightly pungent. It's the moment beer begins to take on its final character. After the boil, the wort must be rapidly cooled. This happens in a plate heat exchanger, where hot wort flows past cold water or glycol in alternating metal plates. Temperatures drop from near boiling to fermentation ready, usually between 10 degrees Celsius and 20 degrees Celsius, in just seconds. In most large breweries, the water used to cool the wort is captured and reused to preheat the next batch, conserving energy. From there, the chilled wort is transferred to fermentation tanks, colossal, conical bottom vessels made of polished stainless steel. Some are the size of small buildings. This is where the magic really happens. Yeast is introduced, either ale yeast or lager yeast. Yeast begins feeding on the sugars in the wort, producing alcohol and CO2 as byproducts. The tanks are fitted with sensors that monitor temperature, pressure, and gravity in real time. If fermentation is too vigorous, pressure is vented. If it's too slow, temperature can be nudged to wake up the yeast. Fermentation can last from a few days for ales to several weeks for lagers. During this time, brewers pull samples to test for alcohol levels, residual sugars, pH, and flavor development. In big factories, this data is fed into digital brewing systems that model yeast health and fermentation curves. If something's off, brewers are alerted immediately. Once fermentation is complete, the beer isn't quite ready. It must be conditioned, held at near freezing temperatures to clarify and stabilize. During this stage, yeast settles out, flavors mellow, and carbonation levels are adjusted. Some factories use centrifuges to speed clarification. Others rely on time and gravity. Filtration may be employed, either with diatomaceous earth, membranes, or cross-flow systems to remove fine particulates and ensure brilliant clarity. For beers that are meant to be bright and shelf-stable, pasteurization may follow, either flash pasteurization or tunnel pasteurization. But not all beer is pasteurized. Many craft-style or draft-only products skip this step to retain delicate aromas. Once the beer is bright, cold, and stable, it's ready for packaging. In large breweries, packaging lines are like choreographed metal highways. Bottling lines can run at 1,200 bottles per minute. Can lines are even faster. Kegs are cleaned, filled, capped, and labeled by machines. Bottles are rinsed, filled under pressure to avoid foaming, sealed with crown caps, and passed through date coders and labelers. Cans are seam locked, rinsed, and pressure checked. Every container is sampled for fill height, oxygen pickup, carbonation, and microbial safety. In some facilities, advanced cameras scan every bottle or can for imperfections in milliseconds. The packaging halls are cold, loud, and almost hypnotic. Conveyor belts twist and curve. Robotic arms stack cases onto pallets. Shrink wrap machines seal entire loads for distribution. Forklifts or automated guided vehicles shuttle product to cold storage, where beer awaits distribution to bars, grocery stores, sports stadiums, and corner shops around the world. But behind the machinery is a deeper layer of quality assurance. Beer is a living product, and even at massive scale, breweries run labs that would rival pharmaceutical facilities. There are microbial labs, sensory panels, gas chromatographs, and mass spectrometers analyzing aroma compounds, esters, sulfur levels, and oxygen ingress. Trained tasters, often called sensory analysts, taste beer daily, blind, and score it against reference samples. A slight change in carbonation or hop aroma is enough to flag a batch for review. And hygiene is non-negotiable. Brewing equipment is cleaned constantly with clean-in-place systems that circulate caustic solutions, acid rinses, and sanitizers through every pipe, pump, tank, and valve. Breweries are designed with sloped floors, airlocks, positive pressure rooms, and filtered ventilation to minimize contamination. Yeast cultures are kept in pure, cryogenically preserved banks and propagated into sterile fermenters. Even the water is treated, filtered, softened, and dechlorinated to ensure it doesn't introduce off flavors. Despite the scale, there's a strange elegance to the whole system. Every tank, pump, sensor, and pipe is part of a carefully designed loop. From raw grain to finished beer, the factory operates almost like an ecosystem, closed, balanced, and tightly monitored. Nothing is left to chance. Even the CO2 released during fermentation is often captured and reused to carbonate the final product, reducing waste and environmental impact. Bacardi all starts with molasses, a byproduct of sugar refining. Once cane juice has been boiled and crystallized into sugar, what remains is a dark, viscous liquid rich in residual sugars and minerals. Bacardi sources its molasses primarily from the Caribbean and Central America, where sugarcane grows in abundance. Shipments arrive by the ton, offloaded into deep storage tanks that keep the molasses warm and pumpable. Its smell is rich and heavy, deeply sweet, slightly sour, with a roasted, almost smoky undertone. Before fermentation begins, the molasses is diluted with pure water and combined with nutrients to prepare what's known as the fermentation wash. Bacardi uses a proprietary strain of yeast, one that's been carefully preserved and propagated for generations. This yeast is key. It's what gives Bacardi its distinctive profile: clean, light, with subtle fruity esters and very low levels of fusel oils. In a dedicated propagation room, yeast cells are grown in increasingly larger vessels, fed on molasses and oxygen, until they're strong enough to handle full-scale fermentation. The prepared wash, diluted molasses, nutrients, and yeast, is pumped into fermentation tanks, towering steel vessels the size of small silos. Fermentation is fast and efficient, typically 24 to 30 hours. During that time, the yeast devours the sugars, converting them into alcohol and CO2. The temperature is carefully regulated. Too hot, and the yeast dies. Too cold, and it underperforms. Sensors monitor every parameter in real time: sugar levels, temperature, pH, alcohol content. In massive control rooms, technicians watch digital dashboards as each tank ferments with machine-like consistency. The result of this stage is not rum yet. It's a low alcohol liquid called wash or beer, usually around 7 to 10% ABV. It smells nothing like rum. It's sweet, funky, raw. To transform it into the clear, potent spirit known around the world, Bacardi moves to the next phase: distillation. Distillation is where alcohol is concentrated and flavors are defined. Bacardi doesn't rely on pot stills, as many small batch rums do. Instead, it uses continuous column stills, tall, multi-stage distillation towers that can separate alcohol with incredible precision. These columns have trays or packing materials inside that force the vapor and liquid to interact repeatedly, concentrating the alcohol while removing unwanted compounds. The fermented wash is pumped into the column, heated from the bottom, and as it rises, different components evaporate at different heights. Light, clean alcohols rise to the top and are collected. Heavier compounds are left behind and drained off. By adjusting the temperatures and reflux ratios, Bacardi's distillers control the exact cut of alcohol they want to keep. The result is a high-strength spirit, often 85% ABV or higher, that's clear, light, and extremely pure, essential for Bacardi's signature smoothness. But pure alcohol isn't rum yet. The next steps, aging, blending, and finishing, are where the artistry comes in. The raw distillate, also called aguardiente, is diluted down to around 60 to 70% ABV and pumped into oak barrels for aging. Bacardi primarily uses used American white oak barrels, many of which once held bourbon. These barrels are charred on the inside, and over time, they impart color, vanilla notes, spice, and tannins to the rum. In Bacardi's aging warehouses, massive barrel halls with racks stacked to the ceiling. Tens of thousands of casks rest in the tropical heat. The climate speeds the interaction between spirit and wood, making even short aging periods highly effective. Different rums are aged for different durations. Bacardi Superior, the classic white rum, may be aged for as little as 1 year before being filtered. Gold and flavored varieties rest longer. Premium products like Bacardi 8 or Bacardi Reserva Limitada are aged 8 to 12 years or more. Each barrel breathes. Alcohol evaporates, a phenomenon known as the angel's share, and oxygen seeps in. Over time, harsh edges soften, flavors deepen, and the rum becomes increasingly complex. Once aging is complete, barrels are emptied, and the rum is evaluated. This is where Bacardi's master blenders, trained experts who can detect flavor differences down to the subtlest note, step in. Dozens, sometimes hundreds of barrels are selected and blended together to create a final product with exactly the right profile. Some rums bring fruity notes, others deliver weight or spice, others still provide structure or sweetness. The blender's job is to make the sum better than the parts, and to ensure that every bottle tastes exactly like the last one, year after year. Now comes one of Bacardi's most distinctive processes, charcoal filtration. For Bacardi Superior and other light rums, the blended rum is passed through layers of activated charcoal, often made from coconut husks, to remove color and certain heavy flavor compounds. This process, inspired by Don Facundo Bacardi himself in the 1860s, strips away rough edges and leaves the rum bright, clean, and smooth. Even after aging in oak, the charcoal returns the rum to a near clear appearance while preserving its vanilla and almond undertones. Once filtered, the rum is diluted with ultra-pure demineralized water down to bottling strength, usually 37.5% or 40% ABV, depending on the market. It's then passed through fine mesh filters to remove any remaining particles, chilled to encourage clarity, and tested for stability. Quality checks are constant. ABV, color, turbidity, aroma, flavor, all are measured in both labs and sensory rooms. Finally, the rum is ready to be bottled. Bacardi's bottling lines are massive, high-speed operations, capable of producing tens of thousands of bottles per hour. Empty glass bottles, custom-shaped with embossed bats and logos, are automatically loaded onto conveyors. They're rinsed, filled with rum under pressure, sealed with tamper-proof caps, and labeled with laser precision. Date codes are printed, barcodes are verified. Every bottle passes through inspection tunnels equipped with cameras and sensors to catch defects, underfills, or misplaced labels. From there, bottles are packed into cartons by robotic arms and shrink-wrapped onto pallets. Pallets are barcoded, logged, and stacked in warehouse zones ready for distribution. Bacardi's logistics network spans continents. From a single facility, trucks, ships, and containers move product across the globe. To supermarkets in Spain, beach bars in Brazil, nightclubs in New York, and resorts in Thailand. Behind the scenes, sustainability plays an increasing role. Many of Bacardi's distilleries use renewable energy, recycle processed water, and recover CO2 from fermentation. Spent yeast and distillation byproducts are often converted into animal feed or used in bioenergy systems. Even the barrels, when retired, may be repurposed for furniture, flooring, or smaller barrel aging projects. Waste reduction is not just about economics. It's part of preserving the legacy of the land and the product itself. And yet, for all this technology and scale, Bacardi's rum still carries with it a certain history, a sense of origin. The company was founded in 1862, and though exiled from Cuba in the 1960s, its roots remain in the tropics. The smoothness of Bacardi rum isn't just a technical achievement, it's a philosophy. Every step, from selecting molasses to filtering the final spirit, is guided by an obsession with drinkability. A Bacardi rum should be mixable, approachable, and endlessly clean on the palate. Jack Daniel's begins with a precisely controlled mash bill of 80% corn, 12% malted barley, and 8% rye. The grains arrive in massive quantities by rail and truck and are stored in silos before being milled on-site in Lynchburg, Tennessee. Corn is cracked into coarse grits. Malted barley and rye are milled finer. The grain is moved pneumatically into huge stainless steel cookers where it undergoes a staged cooking process. Corn first, cooked at a high temperature to gelatinize the starches, then rye, then finally malted barley is added as the mash cools to around 65 degrees Celsius. The malt's enzymes convert starches into fermentable sugars. The resulting mash is pumped into one of 64 fermentation vats. Open-top tanks made from cypress wood, some more than 80 years old. These vats each hold around 40,000 gallons. Jack Daniel's uses its own proprietary yeast strain, maintained and propagated internally since the early 20th century. Before yeast is pitched, a portion of the previous day's fermented mash is added to the new batch. This sour mash technique helps control the pH and microbial stability of the fermentation environment. Yeast is pitched in liquid form and begins consuming sugars, producing ethanol and CO2. Fermentation lasts 4 to 6 days. The mash foams, bubbles, and gives off heat. During peak fermentation, tanks require constant monitoring for overflow and contamination. Automated sensors track sugar depletion, CO2 output, and temperature curves. Staff monitor the aroma, foam height, and microbial activity daily. When fermentation is complete, the liquid contains roughly 7-9% alcohol by volume. This distiller's beer is pumped into column stills, massive stainless steel and copper columns more than 40 feet tall. Jack Daniel's uses a single-stage continuous distillation process. Beer enters the column at various levels, while steam is injected from below. Alcohol vapor rises, separating from heavier components. The alcohol vapor is routed to a doubler, essentially a pot still operating at atmospheric pressure, where it's condensed, reheated, and distilled again. The resulting clear spirit, often referred to as white dog, emerges at around 140 proof. Before aging, Jack Daniel's performs its most defining step, the Lincoln County process, or charcoal mellowing. This process takes place in vats over 10 feet tall, filled with sugar maple charcoal. The charcoal is made on-site by stacking 2x 2-inch thick maple planks into long rows, igniting them with high-proof whiskey and letting them smolder until fully carbonized. Once cooled, the charcoal is ground into chunks and loaded into mellowing vats. The white dog is slowly trickled, drip by drip, through 10 feet of charcoal, taking 4 to 5 days to pass completely through. The charcoal removes fusel oils, aldehydes, and other harsh flavor compounds. The process is gravity-fed and unpressurized, requiring a consistent flow rate to maintain quality. The resulting spirit retains its proof, but emerges smoother and cleaner, with noticeably reduced volatility. Once mellowed, the whiskey is moved into new, charred American white oak barrels, coopered at Jack Daniel's own barrel-making facility. The staves are air-seasoned outdoors for 6 months to 2 years, then assembled, toasted, and flame-charred to a specific level designed to maximize flavor extraction and color development. Each barrel holds about 53 gallons. The inside is blackened from charring, and the wood sugars have caramelized. Barrels are filled at 125 proof and rolled into one of 90-plus barrel houses across the Lynchburg area. These rickhouses vary in size and construction. Some are multi-story wood frame structures, others are steel-clad, but all use passive temperature variation to promote aging. Inside the barrel house, environmental conditions vary dramatically. Upper floors reach 100 degree F+ in summer, encouraging evaporation and faster aging. Lower levels remain cooler and more stable. Jack Daniel's does not rotate barrels between floors, so aging is not uniform. Instead, blending later equalizes the flavor profiles. Barrels are stacked on wooden ricks, often 6 to 7 high. During aging, the whiskey interacts with the wood. Alcohol penetrates the staves, extracting vanillin, lignin-derived compounds, tannins, and hemicellulose breakdown products like caramelized sugars. Oxidation occurs gradually as oxygen seeps through the porous wood. Angel share evaporation causes the proof to rise over time and concentrates the flavor. Each year, a barrel loses 5% of its volume to evaporation. Maturation time varies by product. Old No. 7 typically ages for 4 to 6 years. Higher end expressions like Single Barrel or Sinatra Select may rest for up to 8 years or more. Throughout aging, barrels are sampled periodically. Staff draw whiskey using a thief and assess it by color, aroma, proof, and mouthfeel. No age statement is printed on standard Jack Daniel's because blending is used to maintain consistency, not target a specific age. When deemed mature, barrels are dumped onto a stainless steel trough, filtered through mesh screens to catch char, and moved to batching tanks. Here, up to 200 barrels are blended into a single batch. Before bottling, the whiskey is chill filtered, cooled to near freezing, and passed through paper or cellulose filters to remove fatty acid esters that can cause clouding in the bottle. For Old No. 7, the spirit is then diluted to 80 proof, using demineralized water drawn from the same cave spring used for mashing. Other products, like bonded or single barrel proof, may be bottled at higher strengths or without filtration, depending on the release. Bottling takes place on high-speed automated lines. Empty bottles are rinsed with pressurized air or filtered water. Filling machines dispense whiskey using gravity-fed nozzles or vacuum-assisted pumps. Bottles are capped with aluminum closures, corks, or synthetic caps depending on the SKU. Labels are applied using roll-fed labelers with electronic eyes that verify positioning. Lot codes and production dates are printed in UV ink or laser etched onto the neck. Every bottle passes under fill level sensors and automated cameras. Defective units are ejected immediately. Bottles are grouped into cases, shrink-wrapped, and palletized by robotic arms. Finished goods are transported to climate-controlled warehouses. Logistics teams track SKU distribution globally. Jack Daniel's is shipped to more than 170 countries. Each batch must meet regional regulatory standards. Export whiskey may require separate bottling or labeling runs to comply with EU, UK, or Asian labeling laws. Quality control labs sample bottles from each run and perform gas chromatography and spectrophotometry to confirm chemical composition. Sensory analysts run blind tastings daily to validate flavor accuracy. Any deviation from the flavor profile, too much wood, too much sweetness, excessive ethanol burn, results in a hold or rework. Spent grain from mashing is pumped to presses, dried, and sold as cattle feed. Wastewater is treated on-site using anaerobic digesters and aerobic ponds before being discharged or reused. Energy recovery systems capture steam from cooking and distillation to heat water for fermentation tanks. Charcoal from the mellowing vats is replaced regularly and either regenerated or disposed of as biomass fuel. Spent barrels are sold to Scotch distilleries, hot sauce producers, and breweries for secondary use. The cooperage also reconditions barrels for use in cask-finished products or special editions. The distillery operates under strict federal and state regulation. Every barrel and bottle is tracked with a unique serial number. Auditors inspect warehouse records, bottling logs, and inventory counts. The distillery maintains TTB-compliant records for every production step, from raw grain receipt to final export certificate. Barcodes and RFID tags on pallets ensure traceability from distillation to retail shelf. Security is tight, bonded warehouses are sealed, and access is controlled. Jack Daniel's uses SAP-based systems for production scheduling, batch tracking, and global inventory management. Brewing, fermentation, and distillation data are logged automatically by PLCs connected to SCADA systems. Operators monitor process parameters in real time on touchscreen interfaces. Alerts are triggered if mash temperature, fermenter pressure, still output, or bottling line speed moves out of range. Scheduled maintenance is performed weekly. Sensors check flow rates, valve positions, CIP cycle effectiveness, and tank volumes continuously. Yeast propagation is handled in a sterile lab with HEPA-filtered air, jacketed tanks, and strict aseptic technique. Each batch of yeast is cryogenically preserved and banked in long-term storage. Lab staff test yeast for viability, contamination, and fermentation performance. Infection events, such as wild yeast or lactic acid bacteria, are rare but can halt production for full CIP sanitization of all affected equipment. Sanitizers include caustic soda, peracetic acid, and steam. Safety inspections and confined space protocols are rigorously enforced, especially around fermentation tanks, high-pressure steam lines, and ethanol vapor zones. Mash cookers and fermentation tanks are cleaned between every batch. Distillation columns are stripped and acid washed quarterly. Mellowing vats are emptied and replenished every few months. Barrels are inspected for leaks before filling. Leakers are flagged and re-co-opted or discarded. Every floor drain, gasket, and pump seal is part of a scheduled inspection checklist. The entire facility is USDA certified for food safety and operates under HACCP protocols. Oreo wafer rolls are produced using a dual-stream manufacturing process involving continuous wafer sheet production and separate cream filling preparation, which are later synchronized through an automated integration line. The raw materials for the wafer component are dosed automatically from bulk silos into individual weighing hoppers. The base formulation consists of low-protein wheat flour, high-fat alkalized cocoa powder, refined sucrose, leavening agents, salt, water, and a controlled amount of oil-based emulsifiers. Dry ingredients are metered into a high-capacity horizontal mixer with dual-axis paddles designed for uniform blending. Liquids are injected through precision nozzles mounted at the top of the mixing chamber. The total mixing cycle is programmed between 6 and 8 minutes at varying RPMs, first for dry distribution, then for incorporation of wet components. Dough temperature is maintained between 22 and 26 degrees Celsius. Moisture content is monitored via inline near-infrared sensors and must fall within 10.0 to 11.5% before release to the forming line. Dough is transferred via a covered screw conveyor to a pre-sheeting station. Here, a primary roller flattens the dough into a rough sheet approximately 5 mm thick, which then feeds into a 3-stage reduction system. Each stage includes a pair of high-precision, counter-rotating steel rollers with micrometric gap control that sequentially reduce the dough thickness to 1.2 pounds. Dough tension is maintained using differential speed rollers to avoid tearing. Edges are trimmed continuously using rotary cutters, and trimmings are conveyed pneumatically back to the pre-mix hopper for reintegration. The thin dough sheet enters a continuous baking tunnel consisting of 8 to 12 independently controlled zones. Heating is achieved via direct gas-fired convection and radiant ceramic panels. Internal zone temperatures range from 180 to 220 degrees Celsius depending on the position. Air velocity, humidity, and conveyor speed are continuously adjusted via PID feedback loops. Total bake time is between 85 and 105 seconds. Baked sheets are discharged onto a mesh cooling belt, where ambient forced air coolers reduce sheet temperature to below 30 degrees Celsius within 90 seconds. Cooling is followed by longitudinal slitting. Circular slitting blades mounted on adjustable shafts divide the wide wafer sheet into narrow, uniform ribbons matching the final roll width. Slitting accuracy is maintained using laser alignment sensors. Each ribbon is immediately guided into a spiral roll-forming station equipped with a rotating mandrel. A servo-controlled drum pulls the ribbon over the mandrel, while controlled tension and heat reactivation of the dough surface allows the strip to roll into a rigid, cylindrical shell. Formed rolls are passed through a stabilization tunnel maintained at 65-75 degrees Celsius with low humidity to fully set their shape. Rolls are discharged onto a buffer conveyor which feeds into the cream filling station. In parallel, the cream filling is prepared from sugar, hydrogenated vegetable oil, milk solids, lecithin, artificial flavor, and small amounts of stabilizers. Ingredients are batch loaded into a jacketed mixing vessel with shear blades rotating at 1400 and 1600 RPM. Oil is added slowly to prevent separation, and the entire mixture is heated to 45-48 degrees Celsius. Mixing continues for 10 to 15 minutes until a homogeneous emulsion is achieved. The finished cream is transferred through insulated stainless steel pipes to pressurized holding tanks. Agitators maintain cream fluidity and prevent phase separation. The filling is then pumped to multiple servo-driven depositors aligned with each lane of the wafer roll conveyor. Each nozzle delivers a calibrated cream column into the core of each roll, with filling weights accurate to plus 0.2 grams. The nozzle retracts dynamically during deposit to ensure central cream alignment and full core penetration. Cream-filled rolls pass through a secondary cooling tunnel set to 10 degrees Celsius for 60 seconds to solidify the filling. Thermal imaging sensors confirm internal stabilization before exiting. At this stage, each roll is individually scanned for dimensional conformity, surface defects, and fill anomalies. Rolls not meeting target criteria for weight, symmetry, or visible cream containment are diverted via pneumatic actuators into separate waste chutes. Approved rolls proceed to flow wrapping. Individual rolls are aligned using vibratory feeders and grouped into packaging sets based on SKU configuration. Film is dispensed from reels and formed into tubes by collaring mechanisms. Horizontal seal jaws apply pressure and heat at 135-145 degrees Celsius for 0.3 to 0.5 seconds to close the ends and seal the longitudinal seam. Nitrogen gas is flushed into the package before sealing to displace oxygen and slow fat oxidation. Each wrapper is printed with batch code, timestamp, and best before date using thermal inkjet printers synchronized with the machine cycle. Wrapped products are conveyed to a cartoning unit, where robotic arms pick and place the flow-wrapped units into pre-formed cartons. Cartons are constructed from pre-creased flat blanks that are folded and glued using hot melt adhesive. Carton fill conformation is performed using weight sensors and machine vision. Completed cartons are sealed, labeled, and aggregated into corrugated shipper boxes. Each shipper box is barcoded for traceability and palletized in accordance with standard load configurations. Palletized loads are stretch-wrapped and transferred to climate-controlled warehouse storage. Storage areas maintain relative humidity below 60% and ambient temperature between 18 and 22 degrees Celsius to prevent wafer degradation and cream migration. Inventory turnover is managed via FIFO principles enforced by warehouse management software, which integrates with factory MES and ERP systems for batch tracking. Process validation occurs every production shift. Operators test dough rheology, sheet thickness, baking curve, moisture content, cream viscosity, deposit weight, roll hardness, and package seal integrity. Data is recorded in the batch record along with any machine adjustments or anomalies. All critical control points, including cream deposit temperature, bake time, and packaging seal strength, are electronically logged and must fall within specification limits or trigger corrective action. Cleaning in place procedures are scheduled every 8 to 12 hours. Cream lines are flushed with heated water, followed by alkaline detergent, acid rinse, and sterile water rinse. Wafer production lines use dry cleaning methods for rollers and belts, followed by compressed air cleaning and manual wipe down of forming mandrels. Swab testing is used to verify microbial cleanliness, and ATP bioluminescence testing is used to assess organic residue. Production yield is calculated by comparing in-feed material weight to packaged product weight, adjusted for expected waste. All off-spec rolls, excess cream, and packaging rejects are weighed and categorized into waste type. Cream residue is routed into closed collection tanks for food waste processing, while wafer rejects are disposed of according to facility-specific food waste handling protocols. All mechanical systems, mixers, sheeters, formers, depositors, and sealers are maintained under a scheduled preventive maintenance program. Bearings, blades, nozzles, and conveyors are inspected and replaced based on run hours. PLC logic controllers monitor machine health via vibration sensors, motor load curves, and cycle time deviation analysis. Batch documentation includes raw material lot numbers, machine settings, environmental conditions, operator identification, in-process test results, and any deviations from standard operating conditions. These records are archived digitally and are subject to internal audits, third-party verification, and regulatory inspection. Full traceability is retained for every unit produced. Nutella Be Ready consists of 3 major components manufactured on synchronized but separate production lines: a wafer shell, a Nutella filling, and the final packaging. Each component is produced under tightly controlled parameters using fully automated equipment integrated into a high-throughput, continuous processing line. The outer shell is made from a low-moisture, wheat-based dough formulated to bake into a crisp, blister-free wafer. The dough formulation begins with dosing refined wheat flour, sugar, salt, leavening agents, and a blend of plant-based fats into an enclosed paddle mixer. Dry ingredients are dispensed from silo systems into individual weigh hoppers with accuracy to within plus 0.1%. Liquids, including water and emulsifiers, are metered from heated tanks using flow meters. The mixer operates at multiple speeds for uniform hydration and structural development. Once the dough reaches the required consistency, typically between 22% and 25% moisture content, it is discharged via bottom gate valves into an auger conveyor leading to the forming line. The dough passes through a series of lamination rollers where it is flattened to a precise thickness of 1.0-1.4 millimeters. Differential speed control across rollers prevents tearing and ensures uniform surface tension. Edge trimmings are continuously recycled to minimize waste and maintain dimensional consistency. The laminated sheet enters a rotary molding system. This consists of a rotating die roller with cavity molds shaped to match the profile of the Nutella Be Ready shell. The dough is pressed into the molds using counter-rotating pressure rollers. An adjustable doctor blade removes excess dough from the roller surface. Molded wafers are transferred via a vacuum pickup system to a baking mesh conveyor, which passes through a tunnel oven with multiple independently controlled zones. The oven zones maintain specific temperature gradients between 180 degrees and 220 degrees, optimized for water evaporation, structural hardening, and color development. Each zone's airflow is modulated by variable frequency drive fans to control browning without burning. Baking duration is typically between 80 and 110 seconds. Thermocouples and moisture sensors measure real-time parameters. Upon exiting, wafers are cooled in line using ambient air-blown axial fans, reducing temperature to under 30 degrees Cs within 2 minutes. Simultaneously, Nutella filling is prepared in a separate